Okay. Good afternoon to everybody. Thank you for joining. Can you hear me? Yes. Good afternoon to everybody. Thank you for joining this event, which is the more scientific side of this Giornata della Ricerca in Lombardia, which this morning had a very nice event in La Scala Teatro. So this scientific event is entitled Fotosintesi naturale e artificiale, energia pulita dal sole, and it will feature presentations by the three winners of the prize Lombardia Ricerca, plus presentations by the scientists who will will receive a grant to perform research on the project enhancing photosynthesis. So let me introduce to you Professor Donatella Asciutto, who is the Dean for Research at Politecnico di Milano, who will say a few introductory words about this event.
Thank you, Giulio. It is a pleasure for me being here and welcome you all here, for those who are from Politecnico, but those, especially from those coming outside. Let me congratulate first the awardees of this prize, which is very relevant. And this year was really focused on sustainability, environmental sustainability to improve the quality of life for for better development models. This is an important topic. It's included in the challenges we have today, in the social, technological, environmental challenges that we need to tackle today, and COP26 is demonstrating that this is really a relevant topic, especially for the younger generation, because they will be the ones that will need to be, that are more interested in having a better economical and social and sustainable development of the entire society, which implies also less discrimination and more possibilities for everyone. I do believe technology can play a great role in trying to win this challenge and improve the possibilities of having a more sustainable world. And the awardees demonstrate that through their research, they are already looking into these topics and trying to provide a solution to make sustainability for the production of food and energy something that is really needed and something that needs to be supported in terms of research and development. We know that one of the main problems is the pollution and the CO2 that is that we are producing in all our life, and to be able to reduce or to counteract this production by producing a way to have a better air in our cities, in our world, is fundamental for our future and to tackle the climate change and increase of temperature. We, as Politecnico, research is one of the main pillars, and the sustainability in research for sustainability has been also supported by the National Recovery Plan and the other actions, and we are now including, we have just started with 100 PhDs that are looking into different problems of green technologies, and 40 new researchers, which are starting in this month and the next month. So, and we will continue to invest in these areas in order to be able to provide solution to companies and to society overall. Thank you very much for being here. I'm sure it's going to be a very interesting talks. Unfortunately, I have to go and look at administrative things, and I would prefer to stay here. Thank you very much, and have a good afternoon.
Thank you, Donatella, for your really kind introduction. and for being with us to open this workshop. Now, let me introduce to you Professor Andrea Ferrari, who is a professor, who is a former student, is an alumnus of Politecnico di Milano in nuclear engineering, and he is a professor of nanotechnologies at University of Cambridge, and one of the worldwide, is the director of the Cambridge Graphene Center and one of the worldwide leader in graphene technologies, and also one of the promoters of the great European graphene flagship initiative. So Andrea was presiding the jury who selected the winners of this prize. So please, Andrea, you can say a few words.
Okay, thank you very much. Thank you, Giulio. So as Giulio said, I'm the president of the jury that has been helping and in fact taking the decisions for this prize for the past 2 years. And my task is actually to switch to Italian now, because I'm going to give you the motivation, the official motivation for the prize, so there is no misunderstanding. I read a very short version this morning at the Scala, and then I will also present the 5 investigators of the projects that are going to be funded by this prize. Quindi il Premio Lombardia Ricerca 2020-2021 doveva premiare una scoperta di alto valore scientifico che presenti significative ricadute nel campo della sostenibilità ambientale al fine di un miglioramento della qualità della vita in armonia con il sistema produttivo e la transizione verso nuovi modelli di sviluppo. Le aree tematiche erano la transizione energetica verso fonti rinnovabili, la mobilità sostenibile, l'energia pulita e risorse rinnovabili, l'efficienza energetica, le tecnologie pulite per lo sfruttamento di combustibili fossili, la gestione sostenibile e l'utilizzo efficiente delle risorse naturali, la gestione ecocompatibile dei materiali durante il loro intero ciclo di vita, la riduzione di emissioni di CO2 e sistemi innovativi per lo sfruttamento dell'energia solare e lo scoperto e lo sviluppo di nuovi materiali per la produzione, immagazzinamento e distribuzione di energia pulita. Queste tematiche adesso sono al centro, ma sono state definite dalla Regione nel 2019 e dopo nel 2020 abbiamo dovuto interrompere i lavori del premio a causa degli eventi a tutti noti ed è stato quindi esteso al 2021. Quindi i vincitori del premio sono Pierre Joliot, Marcella Bonchio e Markus Antonietti, per i loro contributi alla comprensione e allo sviluppo dei processi che portano energia pulita dalla fotosintesi artificiale ispirata ai meccanismi della natura. La motivazione completa della giuria è la seguente. Il premio è dedicato al processo vitale della fotosintesi, che permette di immagazzinare l'energia rinnovabile della luce solare sotto forma di energia chimica e molecole organiche e biologiche, fornendo nutrimento e combustibili indispensabili al nostro sviluppo. Gli studi fondamentali di Pierre Joliot hanno permesso di capire i meccanismi chiave della fotosintesi naturale nel suo ciclo di funzionamento biologico, che utilizza fotoni, elettroni e protoni per scindere l'acqua in un processo attivato dalla luce solare. Questo ha dato impulso alla ricerca di sistemi artificiali costruiti con componenti e materiali robusti ed efficienti, in grado di replicare il processo fotosintetico, utilizzando risorse rinnovabili e largamente disponibili come la luce visibile e l'acqua. Sono stati raggiunti dei traguardi importanti nel progetto sul sistema di fotossilazione dell'acqua, ispirato al sistema fotosintetico, che utilizza una disposizione organizzata di antenne artificiali per liberare ossigeno dall'acqua, convertendo quanti di luce in energia chimica, il quantasoma o quantosoma di Marcella Bonchio, e lo impareremo dopo. E nella generazione di idrogeno verde e valorizzazione dell'anidride carbonica in processi ecosostenibili, il fotocatalizzatore polimerico costituito solo da carbonio e azoto o nitruro di carbonio di Markus Antonietti, che integra le proprietà dei fotosistemi naturali in un solo materiale. Quindi, con questa scelta, il premio pone in evidenza la necessità di un approccio interdisciplinare, in questo caso biologia molecolare, chimica e scienze dei materiali, per affrontare sfide urgenti e complesse nel contesto dell'energia rinnovabile e dello sviluppo sostenibile. L'aver svelato alcuni dei processi che negli organismi vegetali guidano la fotosintesi ha portato a radicali innovazioni nelle tecnologie dell'agricoltura e apre strade per il miglioramento della resa fotosintetica. coniugando richieste ambientali, quali l'abbassamento del livello di anidride carbonica, l'utilizzo di fertilizzanti ed altri prodotti chimici per unità di prodotto, con quelle sociali ed economiche, aumentare la produttività primaria e quindi assicurare alimenti di qualità e a prezzi ragionevoli all'umanità. I sistemi biomimetici e i fotocatalizzatori a base di nitruro di carbonio sono già utilizzati per realizzare una fotosintesi selettiva e la sintesi organica fotoredox di farmaci e composti intermedi preziosi. E l'uso della luce solare potrà quindi trovare nuove applicazioni per la sostenibilità ambientale, dalla bonifica di ambienti inquinanti alla purificazione delle acque, al riciclo e smaltimento della plastica, in accordo con i Sustainable Development Goals delle Nazioni Unite. 300.000 euro del premio sono assegnati ai 3 vincitori, quindi per uso personale come premio. Invece 700.000 euro sono destinati ad un progetto di ricerca sotto la responsabilità dei vincitori e in collaborazione con la comunità scientifica lombarda. In tempo record i vincitori hanno già selezionato un progetto che si chiama Enhancing Photosynthesis e l'abstract è il seguente: la fotosintesi ossigenica è il motore che ha mosso l'evoluzione del nostro pianeta e ogni giorno produce cibo, energia e ossigeno che respiriamo. L'equilibrio ambientale dipende dalla fotosintesi, il solo fenomeno in grado di riequilibrare l'eccesso di CO2 prodotto dall'uso di combustibili fossili dell'ultimo secolo di sviluppo industriale e civile. Ciò è possibile perché 1/3 della produzione fotosintesica globale è controllata dall'uomo nei campi coltivati. La fotosintesi artificiale, realizzata in dispositivi di ultima generazione per la produzione di combustibili solari, offre una risposta urgente alle necessità di fonti di energia rinnovabile. Quindi il progetto finanziato affronterà il nodo principale dell'efficienza fotosintetica sia in ambiente naturale che artificiale, dando un nuovo impulso alla ricerca fondamentale sui meccanismi della fotosintesi, intesa nell'accezione più ampia di sfruttamento dell'energia solare per garantire in futuro uno sviluppo sostenibile, pulito e neutro quanto ad emissioni di CO2. I laboratori lombardi che parteciperanno all'impresa, in stretto contatto con i 3 vincitori, studieranno soluzioni innovative per rendere la fotosintesi più efficiente, chiarendone i meccanismi fondamentali e sviluppando alternative artificiali attraverso una ricerca focalizzata sui materiali fotosintetici e dispositivi fotocatalitici. Sarà quindi uno sforzo unitario e interdisciplinare che affronterà l'interazione luce-materia, fornendo la nuova frontiera della biologia sintetica con metodi della biofisica, creando nuovi materiali e dispositivi nanotecnologici per l'energia pulita. I principal investigator selezionati sono Paolo Pesaresi dell'Università degli Studi di Milano, che dovrebbe essere qui, eccolo, Stefano Santabarbara, anche lui l'avevo visto prima, eccolo là, del CNR di Milano, Margherita Maiuri, che è anche qui, del Politecnico di Milano, Silvia Bracco dell'Università degli Studi di Milano Bicocca e Alberta Pinnola, dell'Università di Pavia. E chiaramente i 5 beneficiari di questo premio creeranno un progetto comune, ma io vedo già, solo guardando al panorama del Politecnico, tante altre possibili collaborazioni in questo campo che si possono sviluppare. Quindi invito tutti a mettersi in contatto con i vincitori, a partire da Giulio, Cerullo, Guglielmo, Bassi, tutti gli altri che in qualche modo fanno qualcosa con la luce e con la fotosintesi e con la spettroscopia, per creare veramente un gruppo core di ricerca che possa sfruttare al meglio questa occasione unica che è stata garantita dalla Lombardia. Con questo finisco e invito il vicepresidente della giuria, nonché eminenza grigia della giuria, anche per il colore dei capelli, io non ce li ho, lui li ha grigi, quindi alla fine un mix dei due, a presentare il primo vincitore, che è Pierre Joliot, e dopo a fare il chair della sessione di Pierre. Roberto.
Grazie Andrea. E vediamo se riesco a far apparire le diapositive. Vediamo se l'apparato tecnico. Ecco qui, benissimo. Mi chiamo Roberto Bassi e sono professore di fisiologia vegetale all'Università di Verona. Quest'oggi vi introduco proprio molto rapidamente il professor Pierre Joliot, Emeritus Professor at Collège de France. It's laureate at this research award. Here we can see Pierre in one of his early times, and here is a quote that I steal for him. The research that tells something about his way to do research that is quite atypical in nowadays. Research is an artistic job, one on which you have the right to make a mistake and trying again, and you have the opportunity to make a discovery. You might make small discovery, yet who can say at each moment whether a few years later that discovery will be small or big? This is the case of the discovery of the oxygen evolution and the extraction of electron from water, the same phenomenon that give energy to the planet, give energy to the agriculture, give energy to the geochemistry of this planet and the solar panel. So everything comes from there. So where the activity of Pierre Joliot occurred was in Trèves, Pierre and Marie Curie. Of course, you can see that all his life was a scientific life occurred in these institutions. This is very, very uncommon now that we switch from country to next, from one university to another one. But in this institution, Pierre has been working for 60 years now, always focused on research. Here we can see Pierre and his wife, Anne Grikurov, excellent researcher herself. And this is the family has been a big push in the Pierre Joliot activity. Of course, he's the grandson of Marie Curie and Pierre Curie, 3 Nobel Prize, 2 for physics and 1 for chemistry. And he's also the son of Frédéric Joliot and Irène Joliot-Curie, both a Nobel Prize for physics. Now, in this big pressure, of course, to have this family, this is quite understandable that Pierre changed completely subject and moved from heavy physics to biology. He will tell you about. This is a very small summary of Pierre's curriculum that was born in 1932 in Paris. He was student in biology. He was researcher in 1956 and research director in 1974. I have a very small story about this period of his life, 1985, 1986, in which he was a scientific advisor of François Mitterrand. And it occurred to me several times to answer, since I was visiting his lab, to answer to the phone call and say, well, there is Mr. Mitterrand looking for you. And say, no, I'm sorry, I have no time now. I'm doing an experiment. He will call later. After that, he was professor at Collège de France from 1981 to 2002, and the director of the Department of Biology of l'École Normale Supérieure. Since 20 years, he is emeritus professor, but he's still working in the lab 5 or 6 days per week. So this is Pierre Joliot. And one thing that I learned immediately was that there was something different in his lab. I've been visiting many labs before, but in this lab I saw instrumentation that I saw nowhere else in other labs. All the labs have a standard instrumentation, but Pierre, for each experiment, designed and built his own instrumentation together with an engineer, Pierre Béal, that has been his companion in building instrumentation and new techniques for so many years. For each, here is just 5 of the fundamental methodological paper in which Pierre has been feeding the rest of the research in photosynthesis all over the world. I think that one can say that biophysical photosynthesis is Pierre Joliot, and all the good people working in this field have been working with him, have been his students. So every time he has a new problem, different problem, he built an instrumentation on purpose for that, rather than using already known instrumentation. And now I'm getting to the end to show you that there is a difference between the current model of research, high mobility between labs, city and countries for PhD, postdoc, junior professorship, senior professorship. We are all shuttling around the world, in particular Italian that have been pushed for many years to go abroad for lack of resources in research. Race for publication record and age factor, high competition between researchers, high specialization of subject through scientific life, and laboratory life limited into a PI career. So no continuity of research tradition between generations. When a PI finishes his work, the lab is cancelled and somebody else arrives and do new research. But you lose all the experience like that. The Joliot type of doing research is totally different. Always work in the same building for 60 years, forming many young researchers all over the world. Open collaboration to share technology and even research data with any collaborator that happened to pass for his lab. He was discussing his own most secret, let's say, result with everybody. Developing and applying new technology to different scientific problems. And finally, maintaining the technical and scientific heritage along generation with the new director of this lab. At the present time, the director of the Joliot lab is Angela Falciatore from Naples, for example, that has been since 2 years is the new lab. So what I finished now I've been so lucky to have been admitted and collaborating in many institutions, many good labs with excellent scientists from Copenhagen to Paris, to Geneva, to Berkeley, to Beijing, beside Italy. But since they are all very good, but the way in which I try to have my lab organized and my people trained is the thing that I learned in Pierre Joliot lab. And I think now that we have to listen to him, and I leave the floor to Pierre. Pierre, would you like please to start your presentation? You have to switch, yes, the microphone on. Yes, perfect.
Thanks, Roberto, for this introduction, which summarizes part of what I want to say today. I want also to thank the Lombardy region and the member of the jury for awarding me the Lombardia Ricerca Prize and I am particularly sorry that for health reasons I cannot be with you today. My research career started in 1953. I was 21 when I was finishing my studies at the University of Paris. To get some idea of what research in biology was, I was looking for a non-paid job of laboratory technician. I met my former teacher in biophysics, René Wurmser, at the Institut de Biologie Physico-Chimique. After a short discussion, Wurmser decided that I would immediately start a thesis on photosynthesis in his laboratory. To be sure that I will not escape, René Wurmser put on my shoulder his own laboratory coat and introduced me to Jean Laborel, who was finishing a thesis devoted to Hill reaction on chloroplast. Wurmser has brought in 1930 a major contribution concerning the mechanism of oxygen formation, and wanted to start again research on photosynthesis in his laboratory. A few months later, Lavorel left the laboratory for a postdoc position in the US, and I was then in a rather big laboratory, the only one working on photosynthesis. All my future scientific life was irreversibly decided in a few minutes because I was too shy to make any remarks about this unexpected decision. 67 years later, I am still working on photosynthesis in the same institute. Thanks first to Francis André Bollmann, and now to Angela Falciatore, my successive boss, we accepted that I continue my experimental work although I was retired. Wurmser leave me totally free to choose my subject of research and approach it. My choice was the mechanism of oxygen formation. During my thesis, Wurmser was all ready for discussion, but never wanted to impose any of its personal view. This large degree of freedom was very exciting, but even if I was quite isolated, I have a good idea of what was going in this field through the free basic book Photosynthesis written by Eugen Rabinovich, in which one can find all that was known on photosynthesis. When I began my experimental work, none of the components of the photosynthetic electron transfer chain were identified, and only a single type of photoreaction implying chlorophyll was supposed to be involved. A question always in debate was, what is the origin of oxygen? According to the basic equation of photosynthesis, oxygen formation could only be the result of the splitting of CO2. This was the dominant view during the 19th century and at the beginning of the 20th century. René Wurmser was the first to propose that oxygen formation is the result of a light-induced splitting of water. This concept was later developed by Van Til, to whom it is most generally attributed. According to this view, the equation of photosynthesis should be modified as the formation of oxygen will require the splitting of two water molecules. This hypothesis was experimentally demonstrated by Robin Hill in 1940 on broken chloroplasts unable to fix CO2, and also by Ruben Kamen and co-worker using stable isotope of oxygen. Nevertheless, 25 years later, Otto Warburg, Nobel Prize in Chemistry, and one of the leading scientists in our field, was always defending the theory involving the splitting of CO2. A landmark in the history of oxygen evolution mechanism is the classical experiments of Robert Emerson and William Arnold in 1932. We measure on chlorella oxygen emission induced by short electronic flashes. These flashes were supposed to induce single photoreaction at the level of the chlorophyll. The maximum amount of oxygen evolved by flash was surprisingly low, about 2,000 times less than the chlorophyll concentration. They conclude that oxygen yield per flash was limited by an enzyme present at very low concentration. Different interpretations with opposite structural implication were proposed. The first interpretation proposed by James Franck, Nobel Prize in Physics, was a biochemical model in which all chlorophylls were supposed to be photochemically active. After absorption of a photon, an high redox potential species were generated, able to diffuse, and then stabilize at the level of the limiting enzyme present at low concentration. In 1936, Gaffron and Voll, both physiologists, proposed a daring hypothesis based on the physical concept of excitation energy transfer, a theory first developed by Jean and Francis Perrin. It was known that excitation energy localized on a pigment could be rapidly transferred to a neighboring pigment at short distance. Gaffron and Voll proposed that chlorophyll within the chloroplast were tightly packed and that excitation energy could rapidly migrate in a random way among these pigments. The excitation was finally trapped by a chlorophyll associated with the limiting enzyme, where the primary charge separation occurs. In this model, most of the chlorophylls act as light collector, thus increasing the cross-section of the photoactive chlorophyll. The migration of the excited state and the trapping process should be completed in a time much shorter than 1 nanosecond about the lifetime of the excited state. This implied a solid-state structure not involving diffusion. This hypothesis marked the beginning of modern photosynthesis. When I started my thesis, I was immediately convinced that it was necessary to develop new efficient techniques to measure oxygen evolution. The only method available was the manometric method of Warburg with low sensitivity and slow time response minutes. I built an amperometric technique in which chlorella cells were placed in a flat cuvette. Oxygen concentration was rapidly homogenized by a styling device rotating at 3000 RPM. The current induced by the reduction of oxygen at the level of a negatively polarized platinum electrode was strictly proportional to oxygen concentration. The time resolution of the method was about 0.2 seconds, allowing a clear discrimination between the photosynthetic and the respiratory processes. The actual rate of oxygen formation is the difference of the ratio measured immediately before and after switching off the light. On this basis, it was possible to quantitatively measure the rate of photosynthetic process as a function of various parameters of light intensity and time of dark adaptation. One of the more significant results I obtained was the elimination of dark adapted chlorella by a single electronic flash does not induce oxygen formation. The following flashes induce a nearly constant oxygen emission, close to that measured by Emerson and Arnold. On this basis, I propose that formation of one oxygen atom requires 2 sequential photoreactions at the level of the same enzyme, and that 2 oxygen atoms will cooperate to form an O2 molecule. This hypothesis was at the origin of my future work 10 years later. At this time, I was not aware that the duration of the light emission during my flash was sufficiently long to introduce more than a single turnover at the level of the photoactive chlorophyll. In collaboration with Jean Lavorel and René Delhomme, we observed that during the short transient observed at the onset of illumination, the rate of oxygen formation is linearly related to the fluorescence yield. Minimum fluorescence yield correlate with a maximum oxygen yield. These experiments provide strong support to the excitation transfer hypothesis of Gaffron and Ball. In 1959, I have to leave the lab for almost 3 years to accomplish my military duty. When I came back to science, a revolution has started in our field, which marked the beginning of the current concepts in photosynthesis. Numbers of electron carriers involved in the electron transfer chain were characterized, and the energy was provided not by one, but by 2 photoreactions working in series. The 2 papers I published after my thesis were totally ignored, and I came back to my previous subject without suffering too much of the long interruption of my work. It is at this time that I started my collaboration with Anne that is still happily going on. After having modified and improved the sensitivity of the concentration electrode, I demonstrated that a large pool of electron carrier was localized between the 2 photochemical centers closer to the PS2 reaction center involved in the water splitting process. This carrier has been later identified as the plastoquinone pool. I had the opportunity to present my new result at a meeting in Gif-sur-Yvette in 1953, and it was the first international congress I have attended. At the end of the congress, I was very happy when Bessel Koch, a leading scientist in our field, wanted to visit my lab. Bessel Koch was totally open-minded to new ideas, especially when they come from people working out of the mainstream. Bessel wanted to understand everything in great detail. It was sometimes hard to convince. Following the GIF Congress, and with much encouragement of Bessel, I continue my work on oxygen evolution and chlorophyll fluorescence. In 1965, I developed a new amperometric method in which chloroplasts or algae were settled on a bare platinum electrode. The sensitivity of this method was much higher than that of the styrene electrode, but did not give absolute measurement. I also created a small research group to work on photosynthesis. In 1966, Anne and I arrived in Baltimore in Bessel Koch's lab for a 7-month stay. This relatively short period was one of the more fascinating and fruitful periods of my scientific life. I have worked my new amperometric device, which could be used to detect either oxygen emission or reduction of yield reagent. Most of our work was devoted to the analysis of the redox chain between the two photosystems. At the end of our stay in Bessel's lab, I was invited to present seminar in many US laboratories. This was the occasion for me to definitively break my scientific isolation. After my return at front, I came back to the problem of the mechanism of oxygen evolution. And in 1968, in collaboration with Barbieri and Chabot, we observed for the first time that the amount of oxygen evolved by chloroplasts eliminated by a flash series oscillate with a period 4. The pattern obtained was difficult to interpret because there were a large amount of oxygen evolved on the second flash. I have also difficulty to interpret the large damping of the oscillation. We finally proposed a complex model involving 2 types of memory. In this model, the formation of one oxygen atom required 2 sequential photoreactions. It was the first memory. It was the hypothesis I already proposed during my thesis work. In addition, a conformational change acts as a switch which alternatively connect the photoactive chlorophyll to 2 secondary acceptors placed in parallel. Second memory. We also compare the rate of oxygen emission at the onset of weak illumination on chloroplasts either dark adapted or pre-illuminated by 1 or 2 flashes. In our experimental condition, the fit between theoretical curves computed on the basis of our model and the experimental data was almost perfect, as well as under flash excitation than under continuous illumination. We then rapidly established that some fluorescence and luminescent property oscillate with a period 4, thus demonstrating a dependency upon the number of positive charges stored on the donor side of PS2. In the fall of 1969, Bessel sent me the preprint of his now classic paper, written in collaboration with Forbush and McBlain, in which the 4-step model was proposed. Is it possible to, I think, I am sorry, but I have a figure, but I think I will forget about it. The experimental protocol of Bessel Koch was exactly the same than ours, and it was performed with the amperometric technique I have built during my stay in Bessel lab. The only difference was that the flash used by Koch were of shorter duration than ours. And in this case, no oxygen was evolved on the second flash, and a larger amount of oxygen was evolved on the third flash. The large damping of the oscillation in my experiment was explained by the too long duration of the flash, which were able to induce double photoreaction. I have done the same error in my thesis work. The estate model just implies that splitting of wet and a formation of oxygen molecule require for sequential photoreaction. I immediately adopted the S model, the S-state theory, and at the international conference held in Gothenburg in 1970, in my introductory lecture, I was in a rather strange position to fight against my own model that was supported by many of the auditors. A few years later, I realized that progress in this field would require new approaches using different physical techniques, most of them very expensive. As many laboratories were now working on this problem, I then decided to leave this domain in which I felt that my well-established position at the international level did not at all stimulate my ability to generate new ideas. I never personally came back to this subject, even if later Fabrice Rapaport and Jérôme Laverne, working in my lab, about important contribution on the mechanism of water splitting. I chose to work on the mechanism of electron transfer within the cytochrome B6F complex, and my first concern has been to develop new spectroscopic technique to measure with great accuracy electron transfer reaction in vivo. It has been a long-term project. In collaboration with Daniel Béal, we progressively improved over a period of several tenths of years the sensitivity and time response of this technique, which are always operating in our lab. In terms of basic research, I have been concerned by a large variety of subjects, including all the major protein complexes involved in the photosynthetic process, with an increasing interest in regulatory process. Is it now an opportunity for me, after a long scientific experience, to try to communicate some of my view on research? I have learned very early from my parents and indirectly from my great-parents that research should be practiced as an artistic activity. Our goal in research is to try to find something new, even if what we find concerns only restricted domain of knowledge. I also learned that research is an exciting game, and if I am still doing experiments, it is because I find always the same pleasure to play with my machine as it was the case when I started research. During all my scientific life, I share my activity between basic and applied research to develop new techniques. But I am convinced that these two types of research should be carried out, managed, and evaluated in different ways. Basic research requires a maximum of freedom. A discovery, even minor, is always unexpected and cannot be programmed. Programmation is founded on what is known and is not able to predict the future. Everybody agrees that most of the revolution in technology come from discovery in basic science, and it is sure that authors of the discovery were not aware of the potential application of what they were doing. At variants of basic research, applied research is founded on results and concepts provided by basic science. Programmation is then possible and even often necessary. In the present time, when researchers apply for getting money for basic research, they have to predict the discovery they intend to do and what will be useful of their discovery. To overcome this type of pressure, it's always possible to cheat and to use the money for other projects. But it is more difficult to fight against your own tendency for programmation, often based on some more or less bright intuition. Most of the time, the experimental facts do not confirm your model, but they can reveal unexpected and even crazy results. You have to accept to spend time to check these results that most generally are meaningless, but sometimes this result leads to new and fruitful topics. You have then to jump on it and forget about your initial program. To conclude, if I try to summarize the few successes and the number of failures that marked my long scientific life, it is clear for me that the success came when I started a new subject of research in which I was able to bring some new facts and concepts not in line with the dominant dogma in the field. At this time, no one took care of what I was doing, and then, after a delay, often long, the number of citations of my paper was increasing, just in parallel with my loss of ability to propose new ideas. I am now working for almost 20 years on the cyclic electron process around photosystem 1. After such a long time, the number of citations of my paper is increasing dangerously. A possibility now is to start a new subject. At short term, I am rather optimistic because, in collaboration with a young scientist, Julien Céleste, we are now analyzing the process of electron transfer within the cytochrome B6F that a problem I started a very long time ago. Cytochrome B6F complex is involved in the cycling process. We get recently unexpected results we are not able to interpret in the frame of what is known of the structure and function of the complex. Thus, I am sure that in the near future, I will have a lot of fun playing with this new crazy result. Thank you.
Thank you, Pierre, for the nice. I have to switch on the microphone. Thank you, Pierre. And I think that we have a few minutes for questions. And if there are no questions, I have one myself. So you have been, Pierre, training so many excellent scientists in your career that are now working all over the world. How did you do that? I mean, how did you choose which one was the good researcher and apart from those that were not worth to follow and encourage for this kind of job?
Evaluation is for me the more difficult point in science because it's very easy to make error. The only way to evaluate is to work to somebody, and often you discover that some people who look very bright are not so good, and that some people that look quite slow could have really very good idea. In other terms, I think that the main problem in research is how to evaluate science. In fact, I would prefer to choose the best and also the best subject and the best scientist. But I know that I have no method. And you have to be very careful when you judge people or subject. And I think, from my point of view, that what is more difficult to organize in science is evaluation, because quantitative evaluation, which is now dominating totally the field, is for me a negative evaluation. In other terms, most of the quantitative criterion does not lead to select the more creative scientists.
As you see, there are many people here that share your point of view, Pierre. And I wonder whether there are more questions. Yes, please. We have your fellow laureate, Marcella Bonchio, who wants to ask you a question.
So, Pierre, thank you very much for your vision and your story. And I have one question for you. It's about, according to you, what is the major problem of natural photosynthesis? The one that you would like to solve in order to make it more efficient. If you have to choose one aspect? What would be more important to study now? Thank you.
My answer is very clear. Me, as I think everybody, is totally unable to predict the future. In other terms, I cannot observe the question. What you have to do is to do experiment and to be absolutely ready when something abnormal, non-predicted arrives. In other terms, my opinion is the same that on programmation. If I want to tell you what is the important subject, it's the problem of functional science. Science that I consider at the top, for me, are science of the past. And very often, all the science are the science of future. In other terms, there is always a shift between evaluation, programmation, and the fact. In other terms, I think that the main answer to your question is you should not try to define what is a good subject and what you propose in another term is that predict the future. And I know that I am not able, and all discovery, even if it was small difficult I have done, was always a surprise that I not anticipate. In other terms, I am not able to answer the question.
Okay, we have time for one more question. If there are no more questions, I have the last one myself. Pierre, after you finish with solving the problem of cyclic electron transport around photosystem 1, which one will be your next project at 89?
You know, what you ask me is very dangerous because I have a few projects, but I even don't know if they make sense, you know. For instance, I have the feeling that I have perhaps a method to look to cyclic flow around PS2, but I am perhaps completely wrong, and I have to do experiment, and I am almost convinced if I start experiment on this problem, that I should derive on another subject. In other terms, my feeling, if I do experiment, I try to make more or less crazy experiment in all directions, and sometimes something new could appear, and at this time I focalize on this new subject. But in my way of thinking, it's experimental work which is at the basis of what could look after as a program.
Well, Pierre, that was a really nice lecture and very, very well appreciated from everybody here. We thank you very much. I hope you will stay here, at least in the computer, to listen to the next presentation. Thank you very much.
Thank you very much. I will now ask Silvia Bordiga from the University of Turin, and she was a member of our jury, to introduce the other winner, Marcella Bonchio.
Attends, il faut que je coupe, non.
Andrea, io posso andare? Sì, ok. Good afternoon to everybody. I'm very happy to be here with you and very happy and proud to introduce Marcella Bonchio. Marcella Bonchio started her career at the University of Padova, where in 1993 she received the PhD in physics organic chemistry, learning from her first Italian maestri, Giorgio Modena and Fulvio De Furia.
and later on from John Ewarts at Brown University. While she was a postdoc in Princeton, she learned from Graves, and when she was there, she came back to Italy to join the CNR. And since she was starting the activity, she had all the qualities needed for becoming a very excellent scientist, so restless, curiosity, passion, and patience. And she knows that sometimes we enjoy for success, but most of the time we fail, and we need to be really strong to be able to overcome our failure and to learn from our failure. And in 2001, she became first researcher as the Italian National Research Council, and then from 2013, she is full professor at the Department of Chemistry, Science at the University of Padova. And from 2015 till 2021, she was vice rector for research strategy at Padova. And I heard that now she relieves to left this very hard duty and to come back more to science. So she is devoted to frontier research, a research that goes beyond fundamental and applied research. And this means to the kind of research that is committed to the changes of our common life in order to improve our life and try to solve a major problem. And sometimes we don't know which is the path, but we need to pursue our emotion and also the hard work, which is based on the research that we are going. And in 2011, she received the Prize of Innovation from the Chemical Italian Society. And today, she received the prize Ricerca, Lombardia Ricerca. And I'm very happy, and I leave you the floor. Please, Marcella.
Possiamo fare qua? Devo usare oppure mi metto lì davanti? Si sente meglio lì davanti? Mi sentite? Va bene? Vediamo se funziona, perché è da 2 anni che non faccio presentazioni così davanti alla platea, quindi scusate. No? Forgive my a little bit energy of activation to restart, to lecture in front of this nice audience. So thank you very much, Silvia, for your nice presentation, and thank you to the president of our jury, and thank you to the jury that they did a really hard job in selecting this project, but I am really happy that they actually at the very end choose this topic that is very close to my heart, as you will see in the next slides. Okay, of course I thank you, President and the jury, because this day to me was fantastic, and now we are having fun with science. So thank you very much for this opportunity. So anyway, as you see in the slides, this is the rainforest, and it is shaped as a lung because this is considered the lung of our planet. Okay, and indeed, because the production of oxygen in our planet comes from natural photosynthesis, and as you see, we need to be fast to repair some scars that we have in our planet. And this was also the conclusion of the G20 in Rome. They decided to restore natural photosynthesis, with investing on billions of new trees. Okay, but this will take time. It will take time to restore our natural equilibrium, just using the natural system at that we have right now. Okay, so I have the pleasure to introduce you the group in Padua who is working on artificial photosynthesis our way, and I will explain you what are the guidelines that we are actually following in our labs. And here we are just in front of our department in chemistry department in Padua. It is a group that is rooted in the chemical department, but is a very interdisciplinary group. Okay, we have material science, we have some people that actually are majoring in biology, biochemistry, biotechnology, and so it's a very interdisciplinary effort that we are actually performing in Padua, and this award goes to them. Okay, goes to their passions, their restless effort, their courage in choosing such difficult problems. Okay, and so I dedicate this lecture to them because I think they will make the difference in the near future. And so, to start, I will start from the natural process, okay? And from what we know, the very basic elements that we know from the natural project, okay? What we know is that natural photosynthesis uses water as a reservoir of electrons and protons, okay, that are extracted from water by photosystem 2, so PS2 is the enzymes, and through these photosystems, and you can follow the purple and the red arrows, from these photosystems, electrons and protons are transferred to a second photosystem, PS1, where the reduction part of the process takes place. So in nature, there are two photosystems coupled in the final process. One is dedicated to oxidation and oxidation of water. This is the very heart of the process, and this oxidation process is feeding with electron and proton the second coupled process where we will have the reduction part. And you see, so protons are reduced to hydride. Hydride in chemistry is a form of storing hydrogen. Okay, so this cofactor will be important then for the reduction of CO2, which is a dark process according to to the natural process. So the light phase is here, and the light phase is composed by two photosystems working in couple, one handling the oxidation and the second one handling the reduction. And in this way, water is activated, generating oxygens and electrons and protons for the entire process. So if we have to think about an artificial process, so the best idea that we can have is to make it like a photoelectrochemical cell, okay? In this photoelectrochemical cell, so we have two photosystems, right, coupled. One is a photoanode, where the oxidation will take place, and the second is a photocathode, where the reduction is taking place, okay? And we couple these two electrodes or photoelectrodes by wiring them, and so, by actually having this flow of electron from the two separated photoelectrode. Okay, the current that we generate is the current that is relative to the production of oxygens on the anodic part and to the reduction product on the cathodic part. Here we can choose. Okay, either we can reduce proton and generate hydrogen, right? Or we can also, play a little bit around with CO2 activation, and so actually building an electrode, a catalytic electrode that can really take care about CO2 transformation. Okay, but so we can actually be very flexible, and the products, so the solar fuels that we will be able to generate depend on how we build the catalytic and photocatalytic electrodes, okay? So today, we will actually care about the production of hydrogen. So solar water splitting. On the anodic side, we will generate oxygen. On the cathodic side, we will generate hydrogen. This is green hydrogen because it's made just using renewable resources. So water, which is the primary source of hydrogen, and solar energy, okay? In this way, solar energy is stored into the chemical bonds of this of the oxygen and hydrogen gas, and hydrogen will be actually the energy vector storing the light energy of the sun. Okay, so how can we build our photoelectrode and photoanodes in order to make this process possible, okay? First of all, we have to consider an antenna system, right? An antenna system and a charge separation system, a charge separation that produce voltage, so a charge separation state by absorbing light. Okay, here we build a potential, a little bit like photovoltaics, right? But so if we shortcut this charge separation that we have once that we absorb light, we will have a simple photovoltaic panel, okay, generating current. But we want to go beyond this concept. We want to couple catalyst, okay? When the catalyst will be exposed to the photo-generated charge separation systems, the catalyst will start providing electrons, okay? And if the catalyst here, and we are talking about the anodic part, is a water oxidation catalyst, so a catalyst that can really abstract electron from water, okay? At this place, we will generate oxygen, okay, using solar energy. At the other side, we would need a catalyst that would be able to combine protons and electrons, so generating hydrogen, okay? What is the most difficult part of the process here, okay? First of all, is to find a really good catalyst for water oxidation, and I will show you in the next slides why this is the case. This is not an easy task. Nature has selected one catalyst that is common to all photooxygenic type of forms in nature. And so not many, one in billions years of evolution. Okay? In the literature, there are many artificial catalysts, but really few that can match the efficiency of the natural catalyst. And I will show you in the next slide why this is the case. Okay? Anyway, the major problems are finding a very good catalyst for water oxidation and a very good antenna system that will be able, coupled with the water oxidation catalyst, that will be able to generate charge separation states that live long enough in order to allow the catalyst to perform the catalytic task and not to recombine, fast. So we target to this direct conversion, where, of course, the catalytic center, they are combined with the antenna system in order to have this orchestration of processes, okay? Where the actually rate of oxygen evolution will be combined to the rate of hydrogen evolution so that the recombination will be minimized, okay? And why we started with the water oxidation catalyst? Because this is the most difficult process that we can target in the lab, okay? And why this is? Because we get, splitting water means the breaking of this very stable bond, okay? Water is a very stable compound, so we have it. we can use it, right, in many forms. So breaking these bonds, meaning that we have to apply this thermodynamic energy difference, and more, we have to also to overcome this energy activation barrier that is generally called overpotential. So the extra energy that we have to provide to the system in order to overcome the activation energy of the project. And this is especially high, okay? And why is this? Because this process is a multi-electron process. And multi-electron and multi-proton is a 4-electron, 4-proton mechanism, okay? So we need to remove 4 electrons from 2 water molecules. So we have to combine the transfer of 4 protons. So we are breaking the OH bond, and we have to build a new oxygen-oxygen bond, and this costs energy. So this will be possible through a stepwise mechanism, okay? So in which, you know, we abstract electrons and protons in a stepwise mechanism in order to reduce the activation barrier. And we can be inspired by nature because nature has done this, okay, with the oxygen evolving center. As you see, nature uses 4 manganese center in order to oxidize water through this mechanism. And this is the famous, very famous Joliot-Koch cycle, as Professor Joliot was mentioning to you, in which the oxygen evolving center abstracts stepwise 4 electrons and 4 protons from the water molecules, okay? So we need a very good catalyst, and nature has actually provided us with the perfect one, okay? This can be called the fabulous 4, you know, manganese center that work for water oxidation. So the Fab 4, this, someone in the audience can recognize, you know, this, the fabulous 4 band, okay? So not everybody, but some can recognize it. So the first lesson from nature that we have is that we need a very good catalyst, and that this catalyst has to contain 4 transition metal center, because 4 transition metal center can handle the abstraction of 4 electrons and the transfer of 4 protons. So this catalyst works with an overpotential, so the extra energies, which is about 300 millivolt. And this is the minimum barrier that we can have, okay, for activating water and oxidizing water. Moreover, we can learn other lessons. So the fabulous 4, they are all inserted in a protein environment, and they are surrounded by oxygen-based ligands. They are stabilized, so the oxidation state of the manganese center. In this set, these oxygen-evolving catalysts turn over, so the turnover cycle, the rate of performance of this catalyst is about 100, 400 turnover per second, and the overpotential is around 300 millivolt. Moreover, we can learn that this is not a homogeneous catalysis, so not in solution, but on membranes, okay? So membranes actually are very important in order to confine the process. And what we learn also is that this process in nature occurs every 30 minutes. 30 minutes, 1 hour. It depends on the light condition. After 30 minutes, the oxygen evolving center is dead, okay? And the plant needs to rebuild from scratch the entire protein and the entire oxygen evolving center. So this is something that we cannot do. We cannot afford this energy to rebuild the machinery every 30 minutes. So it will be impossible to apply this kind of machinery in an artificial device. So we have to build more robust and resistant systems in order to do that, okay? And the reason why is this is because, see, oxygen is delivered in the protein matrix at the very heart where the oxygen evolving center is, but it's like to you know, light up a fire in a paper basket, because all around there will be protein residues and sensitizer that can be oxidized very fast, much faster than water, right? So that's why we need the natural system needs to be rebuilt at least every 30 minutes. So in our lab, in those years, we have managed to synthesize 2 artificial catalysts that really work alike the natural oxygen evolving center. Okay, so you can see the structure of these 2 catalysts in these slides. Okay, so both catalysts, they have the active size that is made by 4 transition metal. In the first one, we have 4 ruthenium center, and these 4 ruthenium center are stabilized by 2 cages. You see these structures, okay? These polyhedral structures. These are tungsten oxide residues, okay? These are sort of inert scaffold, but they are useful because they really stabilize this kind of geometry of our catalyst center. And you will see in this kind of shape, the catalyst works and so produces oxygen from water with a very low overpotential, just like the natural system. It works with a similar turnover frequency, so 300 turnover per second, and it's very stable in a very large pH range, from pH 1 to pH 7. But here we have a ruthenium center. Okay, and I will show. We will talk later more about this system. We have also a manganate analog, but this system has 4 manganese center. The geometry looks really alike the natural center, but this is more fragile than the ruthenium analog, so it does not survive many turnovers, and also it survives at a very special pH 5, and it's not so fast as the ruthenium 4 pump. So our best candidate is the tetraruthenate catalyst that we have synthesized in our lab, okay? And this is bridging the 2 worlds of, you know, the natural oxygen evolving catalyst and what is the state-of-the-art catalyst of water electrolyzers. This is an industrial catalyst. It's ruthenium dioxide, okay? But in our catalyst, we have reduced the number of ruthenium centers that we use. These are only 4, and this is the very true active site that works for water oxidation. We don't need more ruthenium atoms. We need 4, because we have to take care of 4 electrons and 4 protons. Okay, so Andrea Sartorelli in our lab, now he is associate professor at the University of Padua, so he was the first during his PhD to synthesize this species, okay? So to tell you the truth, we were aiming to a dimer, okay? You see, the ruthenium precursor here is a dimer. So we were looking for a dimer. For us, was a very important improvement with respect to a monomeric one. 2 ruthenium atoms working together. But we were lucky. We got a tetramer. So a dimer of dimers, okay? And this is produced very efficiently in 80% yield in 100-gram scale. And it's very robust and stable in water in a very broad pH range. You can see the beauty of this structure, okay? So these 2 are the cages of tungsten oxide that they are spectators of the catalytic activity. The water oxidation occurs here at the very center of the molecule, okay? And so how do we know that it works for water oxidation? Well, these are simple cyclic voltammetric studies, so electrochemistry. You can see that each ruthenium center in the structure can be oxidized. So we have 4 oxidation, what we need for water oxidation. We abstract 4 electrons, and when we reach the 4th oxidation state, we can measure oxygen evolution, okay? So we know that this catalyst works with a 4 electron, 4 proton mechanism, and also we can calculate the overpotential that it's required for this activity. And as you see, at acidic pH, this is very low, very close to the overpotential required by the natural system. So we have studied the mechanism, and I will not go deeper in the mechanism, but just to show you that this catalyst can really perform the artificial Koch-Joliot cycle, dealing with 4 electrons and 4 protons. And we have shown this by a series of spectroelectrochemistry studies for mass spectrometry, UV visible, Raman, EPR characterization of each state, okay? So we can follow this 4 state where each ruthenium-4 is oxidized to ruthenium-5, and each water ligand is transformed to OH, and then to oxo, and then to dioxygen, okay? The highest oxidation state that we could not follow and characterize because they are too reactive, so they react too fast, we have this indication by studies, by theoretical studies on this matter. Anyway, and this is dedicated to Andrea Ferrari. So we have managed to support this catalyst on graphene, okay, to make electrodes, and this works very nicely. The most important finding that we had is that the overpotential barrier is not changing. So this is very surprising, because when you actually support one catalyst, so you confine, you block the catalyst on a solid support. So the activation barrier usually for catalysis increases, right? In this case, we maintain the same activation barrier. And the reason is that on this few layer graphene, and you can see the catalyst here, the catalyst stays really well, okay? It is not confined, it's mobile, so it can change the conformation, and it's very stable, so it maintains the structures, and this is why we maintain the reactivity. Okay, so now in the next slides we will see how we manage to interface this catalyst to the light antennas, okay? And we actually were inspired by the photosystem 2. In photosystem 2, the antenna are really surrounding the oxygen evolving center. And so we tried to choose a sensitizer that can really provide this kind of geometry, okay? Moreover, the sensitizer are really in excess with respect to the oxygen evolving catalyst. So what we have tried to accomplish is to select an antenna type system that can really, promote the generation of a photooxidant that can abstract electron from the water oxidation catalyst. So if you want to know more about how to choose the antenna system, please refer to this nice paper by Rink van Grondel, okay? And in this nice paper, the lesson that we have learned is that not only we have to choose the right antenna, but also we have to choose the right geometry, the right spaces, the right linkers and bonding in order to surround the oxygen evolving center, okay? And again, we took inspiration from the PS2, so photosystem 2, and in particular to this coaxial distribution of the antenna system surrounding the reaction center and the oxygen evolution catalyst. So we went back to the Quantasome concept, and we thought that we don't need just a one-to-one system, one sensitizer, one oxygen evolution catalyst in order to win here, but we needed an integrated system where the antenna is shaped according to the function of the catalyst that has to be fitted by light in order to perform its activity, okay? And this was the work by Erika and Francesco. And we chose these perilene bis imides semiconductor why we choose that? Because in water, these are already organized in a sort of, organic semiconductor, in this kind of aggregates, okay? And in the presence of the polyoxometallate catalyst, so our catalyst, these are really exfoliated, and they then provide this kind of encapsulated complex where the oxygen evolving catalyst is just surrounded by the perylene bicimides antenna. So we have identified this kind of complex by many means, but I want to convince you that in water, this kind of complex generates a very powerful photooxidant. So see, we have a very high photoredox potential for the excited state of perylene bicimides. And so we see oxygen evolution. Not only this, but the yield of oxygen evolution, the efficiency of the system, depends on how many sensitizer we actually can allocate close to our reaction center. And the best number, see this curve, the best ratio is 5:1, which is, which is completely in accordance with what we were finding, so that the ruthenium polyoxometallate is surrounded by 5 perylene bicimide sensitizer. And this is why, because the ruthenium polyoxometallate is anionic, and we have an electrostatic interaction of the charged perylene bicimide that actually provides us with a 5:1 complex. And this complex works also on photoanodes, okay? And you will see this is the photocurrent that can be generated by this kind of complex, okay? We have performed the photophysical studies. I will not describe to you this in detail, but just to tell you the results about these studies, that the charge separation state, which is the important state in order to have the activation of the catalyst and the abstraction of electron, is 2 orders of magnitude faster than the charge recombination. So charge recombination is lower. Why is this? Well, this will depend on the structure of our Quantasome catalyst, so of the integrated catalyst. And what occurs in solution is the exfoliation of the perylene bicimides that just provide this Quantasome unit where the catalyst, so the blue part, is surrounded by a shell of perylene sensitizer. This is, of course, amphiphilic, so the blue part is very hydrophilic, the red part is very hydrophobic, and so in water, these organize in lamellae, okay, they aggregate, and these lamellae, they are, they form stacking lamellae, and these resemble the architecture of the chloroplast membrane, okay? We have found some evidence about this, and these are the first images of the high-resolution TEM, where you can find, some fringes here. Okay? We were able also to observe a more detailed fringe patterns, and also, and these studies were performed by the group of Sarah Balz at the University of Antwerp, where you see the bright spots. These are the ruthenium catalysts, so the heavy metal. And so we have a sort of hexagonal packing of the ruthenium catalyst in the in the membrane-like lamellae. And we have lamellae, and this is also evidenced by STM, and this was the work by Thomas Gobbato in our lab, and by the optical microscope also you can see the formation of this membrane that just flow in the water solution, okay? So how is this packing and this assembly occurring? Of course, we have 5 perylene sensitizer around the ruthenium center. So we have calculated, and this is the work of Paolo Costa now in our postdoc in our lab, that a key geometry of a key species would be this lacunary complex, okay? So a sort of vacancy that offers a docking space for further aggregation. And this is known in nature because we have this kind of very special light harvesting complexes that integrate a routine reaction center that they really aggregate through this sigma. They dimerize to this S-shaped complex. So we can imagine that our quantasome is actually providing the same kind of arrangement to a S-shaped complex that this saturates the vacancy and forming a triad, and this triad can also aggregate and forms this kind of hexagonal packing, okay? So we have a proof of this by comparing this kind of models with the PXRD pattern of the solids, and we can conclude by comparing the model with the experimental pattern that we have this kind of aggregation. These are different rows of the polyoxometallate of the quantasome packing, and you see that the ruthenium catalysts are sort of displaced in an hexagonal arrangement, one with respect to the other. Okay? In this arrangement, and if we compare the activity and the photoactivity of this catalyst, we compare to the state of the art of the literature, and especially with the PS2, with the natural system, you see this, we are here, okay, that we can use visible green photon to have a 1.3 efficiency, which is a sort of great enhancement with respect to the literature benchmark and also to the PS2 system. So I just want to conclude by asking you one question. Are you now convinced that we really need a photoelectrocatalytic cell made by two combined and coupled photoelectrode? One is the photoanode and the other one is the photocathode. Well, yes, but not really. Because if we look at what nature does, okay, this is the organization of the natural membrane, okay? As you can see, we have a bulk concentration of PS2, okay, in the chloroplast membrane, okay, that are surrounded, you know, by few PS1 center. Okay, so nature has organized an army here for water oxidation that, and few PS1 surround the membrane. Okay, so how can we do that? Okay, so what we are now trying to reproduce in our lab is actually this. Okay, we are trying to, and this is the work of Francesco, Thomas, Elisabetta, and Ilaria. Okay, they are working together to try really to make this kind of, we can call it lateral aggregation and lateral heterogeneity, okay? So to aggregate a massive amount of oxygen evolving center that can use light, and we can do this by locking these domains using linkers, okay? These linkers are chosen in order to be highly hydrophilic, so also we promote the water access. And with this shape, okay, these are really new results in the lab, we can improve the photocurrent of the new quantasome, the hydrophilic quantasome, the quantasome that is packed and locked in this assemble by at least 3 to 4 times more current. So now I have to tell you that this process was a long one, and we actually enjoyed the collaboration of many labs in Italy, and it was fundamental to have had access to this grant at the national level that actually allowed us to be in contact with the University of Ferrari, Messina, where, you know, we have very strong photophysical experts that they really taught us how to choose and to deal with the photoactivated system. University of Trieste for the carbon nanostructure support, University of Bologna for the electrochemistry, and Electra, the synchrotron in Trieste for the characterization of the material. okay? So I want to thank all these our collaborators and all our young researchers in the lab, you for your attention, and so our vision is to really get rid of the photoelectrocatalytic cell and to have this kind of material tailored in order to be floating in water and be exposed to solar irradiation and provide oxygen and hydrogen on demand, okay? And this maybe can be possible in the near future. Thank you for your attention.
So fascinating by the lecture that I forgot. So my mission. So the contribution is open to the question from the audience.
Marcella, you showed us that you learn from nature to build an artificial system. But given the ample opportunities that we have today to play with genes in living organisms, do you think there will be room to learn from the artificial systems and transfer that knowledge into plants to make photosynthesis more efficient, so to go the other way around?
I think that the two studies are really related, because what we learn also from the artificial system can be translated in order to understand better the natural system, and vice versa. What we know is that we cannot rely on the natural matter, because the oxidation of water is too high and is too demanding. And so there will be no, organic matter that will really resist this kind of oxidative stress. And also, the natural system is imperfect because it will develop radicals, oxygenated radical, single oxygen, singlet oxygen, that is also an oxidant towards, the organic matter. So what we know is that we have to move away from the proteic or the carbon-based structure like the natural membranes, okay, and provide solutions that are more robust and resilient, because the energy to repair costs a lot to the cell.
Marcella, I would like to stay in this subject that you have been outlining right now. So there is a damage. The damage is important and is expensive. Now, the way plants and algae use photoprotection is essentially through carotenoids. Because carotenoids are ancestral in life. So even non-photosynthetic organisms have carotenoids for their photoprotection against ROS, essentially, and many other effects. But maybe that you are an organic chemist, you may suggest some alternative hydrophobic molecules that can be even more photoprotective than carotenoids. And we, geneticists, molecular biologists, we can devise we can devise the way and the enzymes. We can even produce new enzyme for making new reaction in order to produce the compounds that you have suggested. That would be a great. If you can make a suggestion, we are going, right?
So my suggestion is to change way of thinking, okay? Once you produce radicals in the system, radicals, they react with no activation barrier, okay? So whatever is around, they will attack, okay? in order to win with an antioxidant, so a sacrificial species that you add in the environment in order to be attacked by the radicals, yes, you can do, but the concentration of this kind of photoprotector should be really high, and in order to, win over, the external attack, which will be favored because radicals will be produced there where the proteins are. Okay, so you don't win with this. You don't have to produce radicals, okay? Or you have to avoid their formation by introducing mechanism that can really, block their formation. And what we have learned in combination with, collaboration with Thomas Morosinotto, is that when we add an artificial catalase to the algae, okay, so a catalyst that can decompose hydrogen peroxide to oxygen, avoiding the formation of radicals. So we go to the origin of radical formation and we block that mechanism and we bypass that by just deactivating the hydrogen peroxide that is the source of radicals by decomposing to oxygens. So we have found some interesting results adding this artificial catalase to the system. Catalase is enzymes that decompose hydrogen peroxide to oxygen. I think that this would be a system, or if you want some photoprotector, I would study a photoprotector that acts as the catalase, so decomposing hydrogen peroxide. Or you change the oxygen evolving center to some perfect mechanism that does not involve formation of hydrogen peroxide.
Or a comment. I perfectly agree that the biological material have got the bad effect of wanting to die, and especially photosystem one turnover very quickly. But other than radical, is it possible, you think, or can you consider that is the potential itself of the S states which could attack the protein directly, so that you formally oxidize, you get to make radical off the protein without being mediated by fusion species around?
Maybe, yes, that would be also a mechanism. It depends.
Because in that case it will be completely unavoidable, and that's probably why the...
Yes, the protein that is really close to the oxygen evolving center. Yes, of course. The oxygen evolving center, so the catalyst passing these 4 states, we reach high oxidation states, so powerful oxidant that can attack the protein itself, just localized. And in the presence of oxygens, this will go to peroxy radicals and then to radicals. Yes, that's very true.
Thank you for your nice talk. 2 questions correlated. The first one is, in your opinion, how much time are we far from the solution and for an industrial application? And the second is, according to your understanding, do we have in the world the main raw materials to create a so large amount of this kind of artificial leaf that would allow us to produce the whole amount of required hydrogen for the sake of humankind?
So how far we are from the final results, this is a difficult question, okay? So we are progressing so fast, okay, that I think we can have some intermediate solution to that, in that direction, before, reaching, the dream, where you actually have this little power that you just disperse on water everywhere in the world. You don't need to be connected to wires, and you will have just the production of the 2 gases, okay? So there are already some devices that have been produced around this concept in Japan, for instance. But yes, we are a little far from the final solution, but we have learned many things that will allow some intermediate advancement, maybe passing by from the photoelectrocatalytic cell. Then, do we have enough material? Okay, this question as another question related. Is the material stable enough that we can recycle it? Okay? If this material will not be decomposed, and from our test, we don't have the decomposition, the catalyst and the sensitizer are not decomposed after many cycles, okay? So you can exploit the system in a long-term activity, and so this depends on the life cycle analysis of the system, okay?
Okay, so very, very nice talk. Thank you very much. Just a curiosity, it is possible to isolate the Quantasome building block or not by playing with the different solvent? Because if I understood well, this hierarchical structure is formed in water, and you can observe the formation of these lamellae. But I am curious on the fact that if it is possible to isolate the single building block.
So this question is very interesting, and gives me the opportunity to tell you that if we build the Quantasome, so the single unit in organic solvent, okay, with a little bit of water or whatever, and we try the photocatalytic activity of the isolated species, okay, the system is not working. So we need the architecture, okay, as the PS2 needs, this lateral packing in order to be active, okay. In order to study the solubility and the organization and how to tune this organization, we are now, functionalizing the sensitizer. This is a molecule. Chemists can do that. We can synthesize different molecules and different sensitizers, and of course we will install some different functions that will provide a better solubility in mixed solvents in order to study how important is the aggregation state of the system.
Okay, thank you so much, but I think that we have to move on with the program, and we thanks once again Marcella for the nice contribution.
Thank you very much. We move forward with the presentation of Markus Antonietti. And I call Maurizio Prato from the University of Trieste and Bio Margune in San Sebastian to chair the session and to introduce Markus to us. Thank you, Maurizio.
Buon pomeriggio a tutti. It is a great pleasure to introduce the third speaker of today and the third winner of Premio Lombardia, Markus Antonietti. As you can understand from the name, Markus has Italian origins. If I remember correctly, from Piemonte region, but he's German. He studied chemistry at, well, one cannot be perfect. He studied chemistry at the University of Mainz, where he became assistant professor. And then he became full professor at the University of Marburg, and then at the University of Potsdam, which is near Berlin, where he's also still currently director of the Max Planck Institute on colloids and interfaces. He received many awards. He received doctorate degrees in many places, and I'm not going through all these awards. I want only to mention that even if we don't believe really in numbers, but Markus has an H index of 190, which is really impressive. And he is one of the most influential scientists, especially in material science. And so he is the one of the people who gives directions to people, to young people in particular, and also how to solve problems. And so we all look forward to his talk, and I give you the word. Please, Markus.
Thank you very much, Maurizio, for keeping it short. Indeed, I have to excuse that although from Piemontese origin, my father was a refugee after the Second World War, and he met my mother in a refugee camp. And when I dropped out of my mother, it was Germany. So this is why I became German. But I have to excuse for that. Nevertheless, I hope the Italian genius is still partly in me. Yeah? And I can prove, of course, that. I see myself indeed more than as a teacher, and that's what you correctly said. I had the pleasure to work with hundreds of students, literally. And of course, I have to express thanks at the beginning. First, of course, to the committee, to this wonderful prize. It's special. It seems special. And as compared to all the other prizes, this was something else today, absolutely. But I have to express also thanks to my students, my wife, and as already Marcella said, this prize, of course, is mostly for the family and not only for the grandfather of all. I want to entertain you. I want to save time. Yeah, so I want to hear also young people. So this is why I started my talk really like an exercise. And this is what I usually do. Yeah, we know indeed that photosynthesis was created on Earth. It's a chicken and hen problem because I am sure that photosynthesis precedes biology. For biology to run a system, it has to find something to steal, of course. Yeah, to have something alive without energy generation. To invent photosynthesis is the wrong way around. So the question is, could there be something like photosynthesis, elemental photosynthesis, long before life? Yeah, and how would it look like? And this is just a play of mind. It doesn't mean it has to be truth. But we played this game, and at the end, if it comes up with something meaningful, at least it was useful. And that's all what I say. So don't believe too much that everything I tell you is true because it's too long ago. Yeah, but I tried to find the first peribiotic, so through the creation of biology, photosynthesis. And it's very good on a long day, on an evening, to keep you awake. So this is indeed how it starts. We are lucky. Mother Earth has a second try. So about 4.5 billion years ago, two protoplanets collided, and they melted down everything. So Earth and Moon system was created in a big bang of, well, planetary dimensions. And the metaphor, of course, is this wonderful Theia coming to Hyperion. And you know that this type of collisions creates a lot of energy. Yeah, so you see everything is okay. The question is, how did life afterwards start? And this is easy to find out because we have carbon residues everywhere. And be aware that biology creates a different C12 to C13 ratio than chemistry. You always have a depletion. This is due to the vibrations. Yeah, so in biomass, it's -20, this depletion. Yeah, and natural, I mean chemical photosynthesis is -5. And the super old carbons we find -18. So the assumption is very good that most of the carbon we have on this planet is from biology. Yeah? And it's 3.8 billion years old. So this means practically 200 million years after the planet turned solid, photosynthesis or biology-like photosynthesis was there. A rapid invention, it cannot be complicated. It must be easy. Good news for stupid chemists. Yeah, of course. How it was created, we even know the conditions, because if we go back to that time, the geological area was called Hadean, hell-like. And it was really an awful place on Earth. So you see the conditions. The oceans presumably had a temperature of 200 degrees centigrade. We had regular meteor impacts because the face of the moon was created those days. It was super highly acidic, yeah, full of dissolved iron, 2+. The world was reductive. The atmosphere, presumably because of CO2 and ammonia, 20 bars, more like Venus, yeah, And you tell me that biology of nowadays type is created at these conditions. I think not. Yeah, but who knows? Yeah, as I thought you would play around. The chemical components we have are written down below. We have nice chemistry. It's the chemistry of the Miller experiment in the very end. So we have HCN, H2S, ammonia, everything, as I already said, very reductive, no iron 3+. Oxygen in the atmosphere is very late, I have to say. So the first 1 billion years, we did not need PS2 at all, because there was so much iron 2 in the oceans that you could run, so to say, the type of CO2 fixation only on the base of iron 2. And also this we know from geology, because Australia was precipitating out of the ocean those days. Yeah, iron 2 dissolves in water at these conditions, iron 3 does not. Yeah, so we know that Australia is indeed a continent created presumably due to biology, which means oxidation of iron while binding carbon at the same carbon dioxide at the same time. Yeah, quite a different picture. Yeah, and you see about 1.5 billion years we had the so-called oxidic catastrophe. The world turned oxygen in the atmosphere. Most of the primary system, when we removed, died because of oxygen. And this is, of course, the moment where we have to invent a different chemistry, because now we move slowly from highly reductive conditions to the neutral conditions we have nowadays. So expressed in redox potential, we are approaching now zero redox potential, and all the ions, all the minerals you know today, of course, are a product of this oxidation process. Chemistry has some things to say because they're so-called molecular fossils. Molecular fossils are things you find in everything nowadays, even at places where they're not necessarily used. And adenine is a very good case. You know, biology uses adenine at all conditions. Yeah, so we have ATP, and it's a nuclear base. Yeah, so this is presumably very near to the first trials of polymer science to make something like photosynthesis. And you should know, adenine is noble. So the question asked today, do we have a molecule surviving plus 2.2 oxidation conditions, is to be answered with yes. Most nuclear bases do. Mother Nature decided to write the information of life into single molecules, and think about an oxidative sensitive molecule where you write your information inside. This would be bad storage. So be aware that DNA must be oxidation stable, because else it would be useless. And if I believe in textbooks like Jurassic Park, after 150 million years, you can take out dinosaur DNA and create life, so it should be rather stable. But don't believe your Jurassic Park, of course. Yeah. We know a lot of this chemistry from so-called black smokers, which are still there in the deep sea. The conditions there could be very near, indeed, to life. We also know it, of course, from nowadays functional system. This is something like a crime case based on evidence. So this, of course, is the elemental unit of a cytochrome. And if you go now through quantum computing, you see that the iron in the middle is meaningless for the transition. The real thing is this little ring of iron and carbon around, and this is this organic semiconductor. This system already, in principle, can stabilize anions and cations, so it's some type of this DA thing Marcella was talking about. So looking into space of carbon and nitrogen molecules was a nearby hint. And chemistry, to make that, is nitrile chemistry and polymer science, so this goes with the other information I gave you. This is our simplified way to do it. And again, this is definitely not biology, but biomimetics, because this obviously has not a 4-fold symmetry, but a 6-fold symmetry. And this is the famous carbon nitride I will talk about. It's an old molecule. It's the eldest polymer described in scientific literature, because already Justus Liebig, about, how long is this ago? 200, too much to calculate for me. Yeah, so it's quite long ago. And you see it's a 2-dimensional polymerization, and it's based on urea. The molecule in the upper right is cyanamide. This is urea at 200 degrees centigrade. Urea is not stable. It eliminates water, it creates cyanamide, and the cyanamide is doing a 2-dimensional polymerization, creating a single layer graphene, however with holes. And the holes obviously are everywhere because of the nitrogen, you have to have a connectivity problem, and nature is solving the connectivity problem like that. I don't want you to fall asleep. So this is... How does that one? Click on the picture. So this is stolen from the internet. It's an old marketplace experiment from medieval times, and it's called Pharaoh's Serpent. Isn't that beautiful? This is the synthesis of carbon-19. The stuff is burnt in fire, is born in fire. It creates obviously liters and liters and liters out of 2 grams, and the synthesis is easy. And if you ask me for expenses, it's the expenses of urea, which is a mass chemical, and practically no processing. It's an elimination. You end up with about €3 per kilogram. So it's simple. Okay, born in fire, simple, it looks nice, and then of course we go on one step. This is now the chemical synthesis, and you see it's yellow, it's a semiconductor. The extinction coefficient of this stuff, expressed in Lambert-Beer units, is over 350,000. So 100 nanometers are absolutely enough to collect all the light. Sorry, Marcella, we don't need antenna. This is an antenna. So the semiconductor is an antenna. It's brutally colorful. And if you believe in quantum calculations, you see the homopotential is at plus 1.8 volt of this system. This is really stable, yeah? And obviously it engulfs water and oxidation and water reduction. So in principle, this alone could split water. So we made a molecule from a urea, which in principle would be able to split water, 1,000 little details assumed. It splits water. This is the 2009 experiments. It also generates oxygen, I should say. However, I dislike this old experiment in spite of being famous because we still need platinum. And already these days, platinum is a classical hydrogen evolution catalyst. The system stores electron-proton pairs and does nothing with it. So it's a classical sponge component because electrons go in, protons go in, and you need a platinum to liberate the hydrogen. But we don't want to have platinum because platinum was not on the primary menu of evolution. Yeah? So all these metals, no, yeah, because they're rare. We heard today 6 atoms were used to create life. It's a little more, yeah, but about 6 elements are okay. It's a semiconductor. You can do all the things you can do with silicon. You see, this is photocurrent. This is lifetime measurements. You can make electrochemical analysis, and you see one of the rare cases where theory exactly predicted the right positions of HOMO and LUVO. It was not so complicated because it just was composed of C and N. I just want to show you some of the primary reactions of evolution. Because when I tell you it does not liberate hydrogen, electron-proton pairs are stored, maybe it can do other chemistry. And this is the interesting chemistry in it, because, for instance, it can form sugars. This is photocatalyzation. It's not a trivial reaction. It looks simple. So you take a ketone, you add an alcohol, and what is happening? Thank you very much. You're too perfect. Yeah? Is this one? This is the real thing. The quantum yield of this reaction is 70%. Yeah? Practically all stored electrons are used for this chemistry. You don't need platinum, you just need the ketone, but then it does chemistry, of course. And you see turnover numbers, yeah, conversion, not very impressive, but the reaction simply is a quite relevant reaction to create the molecules we later will build life upon. Because you think all the thing is there to build a protein. It's not. It's even unclear how protein was built. Yeah? Maybe this is an option. This is thioamide synthesis. It looks like an amine, and in this case, electrons are taken up by sulfur. And you know, of course, the name vulcanization, so sulfur was there a lot at the beginning because volcanoes, meteorite impacts. We didn't have sulfate, we had sulfur those days. So what do? We create indeed a peptide-like structure from 2 molecules of that using that as a coupler. And if you know a little experience in organic chemistry, you know that this one exchanges against a protein. It's a peptide synthesis. Yeah? Again, conversions, 99, 80%. So in the good cases, this type of chemistry always works with 100%, and the yields for the components are given here. So obviously, we can use this very, very simple molecule to couple two amines in a photoredox to a peptide. 99% yield is enough to form polymers. That's the good thing. So the good news is we can make peptides now from photoredox chemistry. Leaving a little natural space and going to technology. So this is toluene, this is sulfur, it's the same reaction. This molecule is what I call the poor man's anarchist toy kit. This is a devulcanization agent. Industry needs it to dissolve rubbers to make them liquid and to let them reharden. It's a sulfide-sulfide exchange. You take this liquid, you put it on a car tire, it melts down to the concrete and rehardens, of course. So it's not very nice. Yeah. We went through the chemistry. It works with highest yields, 88%. So you can make this complicated molecule on the base of toluene and sulfur only by photoredox chemistry. And this is what I tell you. Nature always uses proton-electron pairs, and you don't need to generate hydrogen from that with a platinum. Sometimes you can use organocatalysis and just do exciting chemistry with it. Co-worker, young people, Sasha Savateev, he's from Ukraine, invented 19 new reactions unheard to mankind without this catalyst. So obviously the power of a catalyst with very strong oxidation potential is very high. This is the last one missing, and you know that, or I should say this is a photo-Hansch reaction. So Hansch ester is one of the famous molecules which is a synthetic hydride transfer agent. So this is now for the first time hydride, H-. Yeah? You take a boring ketone, yeah? You run the reaction with a typical catalysis, and what you get in the very end, isolated yields, yeah, are in parentheses. Where is parentheses? Do we have it? Yes, here it is. Yeah, 85–95% of the system created by a reaction. Rather complicated molecules build up of ammonia and ketones and alcohols alone. And if you have Hansch esters, you are in the very end, in the beginning of a hydride transfer chemistry. Now you can start to feed enzymes. All that done by a stupid molecule based of urea. It's getting too much, so there are many reactions. I don't want to bore you. I want to save time for the young people. I want to talk a bit about the extension bonded principle. Now we leave indeed the space because I was not happy with performance. Because we need more color. We only can use blue light. 90% sounds cool. Yeah, it's quantum yield. But only about 7% of the light is blue. So we have to move the whole band a little into the greenish, reddish region, of course, and this we do with different condensation motives. The polymer chemistry is in our hand. Yeah? Marcella showed on that supramolecular pre-alignment of structures by the packing interactions also changes the color, so you can play with organization. And of course, what we do a lot, but I cannot tell you, is heterojunctions and non-hybridization. This is essentially the idea to couple two systems, to let them work as a set scheme, which is the natural solution in the very end. So what do? We have a new molecule. It's called CNX. This sounds like Elon Musk, so it's impressive, the name. Yeah, but it has indeed an oxidation chemistry, now oxidation potential of plus 2.5 volt. And now we are leaving the ordinary regions of chemistry because my colleague Burkhard König can do indeed oxidize nitrate. And nitrate as such is an oxidation agent. It cannot be oxidized. Yeah? You can oxidize chlorine to chlorine plus. And this is also quite unusual because you start to do very strange chemistry. What I like to show in this case is the incredible beauty of the structures. So this is a hexagonal crystal of the CNX. You see a packing. This packing here is 1 nanometer. And this is the regular alignment of the superpores. So what you see here, whenever it's white, yeah, it's pore. Whenever it's black, it's matter. This is, don't hurt people. Yeah, the stacking of the heptazines. This is 1 heptazine. So this is, and you see, the stacking is tighter than graphene. It's 8% tighter than graphene. My organic chemistry teacher, but it's long ago, told me you cannot pack things without binding tighter than graphene. There's a minimal distance of course, the electron cloud. The answer is there is a donor-acceptor interaction between the layers binding it. So this is the indication as an inorganic chemistry for an additional binding mode. And all that together, of course, creates beauty. This is the crystal structure. It's indeed a superpore, so it's a little bigger, and indeed creates oxygen and hydrogen without catalyst now. So we're cheating. Marcella taught us that the liberation of oxygen relies on 1.2 volt, and now I have plus 2.5 volt. So this has such a high overpotential that's a shotgun. I don't need catalysis for that. It just liberates because it wins so much energy even without it. So this system splits water without any cold catalyst. Let's go to some data, but one slide is missing. Good for you. Now I do something scary at the end. And of course, you know this guy. This is Frankenstein, and Frankenstein was constructed from leftover parts, and then we used a little electricity and brought this guy alive. So this is exactly the name of the project, Frankenstein project. And we use, of course, a little light to bring things into life. The idea, however, is not so dangerous as creating a big person, because the only thing we really want to do is to set a turbo on an enzyme. So we take an enzyme. Enzymes have wonderful reactions. So for instance, this is a classical peroxidase, but you see they work always with a cofactor. So to run something, we have to put energy in biological currency. So if you're more closer to business, light is a currency of energy. And now I want to transfer the light with the carbon nitride into the biological currency. Idea, of course, is that I inject a lot of carbon nitride in my cells. I go out, NADH is created, and I don't have to take food anymore. This was a joke. I love Italian food. So the answer is simply it's an additional energy contribution, because if you can create NADH in a bacterial consortium outside, someone will eat it, I'm very sure. Good. So what did we do? Light, carbon nitride, and you see indeed here, this is NADH generation yield. And this is carbon nitride alone. It does not really work. This is carbon nitride with a mediator. This is disappointing because it contains a noble element again, but you see we can easily regenerate 90% of the NADH in around, 10 to 60 minutes. If you go through the numbers, it means, again, an apparent quantum yield of 80%. So the transfer of a light proton-electron pair to NAD to create NADH is an incredibly fast and efficient process. You can measure it in the NMR tube. We're not talking nanomolar or micromolar. This is millimolar. So it's real chemistry because it's so fast. And again, same data. And what we do now is a model experiment, of course, to see what we can do with light. And what we are doing here is indeed pyruvate to lactate. It's a stupid reaction, but it's a chiral hydrogenation. So no one wants to do that. But you see, we can quantify it quite easily. This is the lactate concentration, and you see linear growth of the system, complete conversion after 6 hours. We did a chiral hydrogenation by the combination of light and an enzyme. Quite Frankenstein. Some attentions of you will find out that I talked about 10 minutes, and here I'm talking about 5 hours. What did we do? We did just a little NADH inside. So we added 1% of NADH in correspondence to the amount of pyruvate, which means every NADH was turned around 100 times to drive the reaction. It's currency, and currency, of course, is running around. So whenever NADH was used, it was recycled like that, and obviously we indeed can feed that biology, which in this case is an enzyme. This is cool. I like that. So at the end, I promised to leave time for the young people. I think carbon nitride and the whole family, there are many like that, are organic semiconductors. This is important to note. It's a very simple structure, and it's brutally stable. Some of these systems survive in technical machines for 2 years without any decomposition. You cannot oxidize it. It's impossible. The only weakness of the system is base, strong base. Then it dissolves. Yeah? We did a lot of chemo and photocatalysis, and the interesting thing is many of the reactions we need, indeed, for early life biology we can create with this system. And it was certainly not carbon nitride, which was raised, but something similar, condensed from other molecules or co-condensation. We don't know that, but we have to play maybe another 150 million years to find the right system, because this is about the time it took for nature. Yeah? The nude area redox here was still available, is there. We can do deep oxidations. Deep oxidation means iron 5 oxidation, because at plus 2.5 volt, you really have strange elements if you bring them near. So iron gladly throws away 2 electrons, yeah, just to be on the same level as the carbon nitride, and then, of course, is doing interesting chemistry. It's there, yeah, and I like the concept of hybridization with biology, but here I have to admit I'm a too bad biochemist to really do that, so I rely on corporations. Yeah. So I already expressed the gratitude to my students to doing that, but now I express the thanks to the audience. You stayed awake. Thank you very much for that, and thank you.
Thank you very much, Markus. Do we have questions? Yes, Roberto. Is there a microphone?
Thanks, Markus. He's doing everything by himself. I mean, it's more a comment than a question, in the sense that I thank you for letting us perceive that although life comes from a type of chemistry, there could be other chemistry, and as the present life forms are the residual after selection, maybe we could have had another life in this planet, and when thinking at that, why do you think that the type of chemistry that you have been describing right now, let's say, didn't make it in competition with the normal biochemistry that we have?
Thank you very much for this very good question. I was using a hook. Yeah, this was, of course, I hoped that you asked this question. It was after 5, and I just want to keep your imagination awake. I think the reason why this chemistry did not exist is purity, because I need pure urea to create the monomers, and then they condense to this scheme. And whenever there would be something similar, a nitrile, a ketone inside, it would copolymerize. And as I think we always talk about primordial soup, the planet was at the beginning very soupy. Clean chemistry is not the way to go. We use clean chemistry, of course, to quantify data to make them reproducible. Yeah. So I just say life might have been, or another type of life. It's a good vision, but the real secret is in dirtiness. Yeah. So we need to do some copolymers, and then I think we will even outpass these properties. But there's a large variation of copolymers, and being dirty, yeah, is maybe not the best approach.
Other questions? Please.
Thank you. What do you believe are more promising? Solid state, like porous materials, or either periodic or amorphous, or crystals, or something with discrete systems? So it's a very general question, obviously.
I think it's one of the key questions for young people, because you have only a limited time to try. and you want to be successful, and even if you don't want to have a high age index, you need good papers. Yeah. So I think for the lifetime considerations Marcella was mentioning, we need solid state structures, because indeed the turnover number of heterogeneous catalysts is much higher than the one of homogeneous catalyst. Yeah? And again, photocatalysis, as we run it, has partly turnover numbers of 10 to the 10, 10 to the 11. And you're invited to check for homogeneous catalysts. You will find no one doing that. The good thing with solid state structures, as long as it's biomimetic, even at some type of self-repair is existing, because you have a certain pulling energy into the solid state structures, the crystallization enthalpy. So even if the reactions dissolve it for a short time, the probability that it reforms maybe somewhere else, yeah, is very, very high. So calcium carbonate you dissolve in acid, but you have an average pH will reprecipitate again. This is the argument. Biology is unbeatable, now biocatalyst, when it's about complicated reaction, value molecules, chiral reduction. Here I'm hopeless as an inorganic organic chemist, and whenever I want indeed a chiral lactate, why not taking an enzyme and doing the high value operation in one shot? Yeah, so I think indeed biology is bad to make acetone or something like that. I would not do that. Yeah, and except wine, I would not even do ethanol with biology. Yeah, but in the secret, again, we talked about is in the dirt. Yeah, so in wine, we take all the side products, and if it's well composed, we enjoy the wine. Believe me, ethanol in water does not taste. My students tried a number of times, and these experiments failed. Yeah. So I believe strictly in heterogeneous catalyst, homogeneous, same story when we do a special thing. But even there, I think the hybridization, yeah, which means near surface catalysis, yeah. Radicals, for instance, are a danger in free solution, are no danger along surfaces because they form so-called surface-bound radical pairs. It's a heterogeneous effect. It's in, so to say, the radical pairing over the heterogeneous interface, and these are things you cannot do in solution. But I wanted to win time for the young people. Maurizio?
Where are the young people? These are all
to present.
Ah, to present.
Kick me out and present.
No, I was just curious to know what is X in CNX.
This was no hook. This was a secret. In the very end, the thing we wanted to do, which failed, was a boron. Yeah, because in boron we add some Lewis acidity to the system, and it's well known that the boron-nitrogen pair is even further lowering the HOMO level. So one of the most stable compounds is boron nitride, and interestingly, boron nitride can be copolymerized with nitrogen. So it's in a ternary system. It failed. And now we just found something else, and we are back to the Joliot principle. Sometimes you try one thing, you find the other, it's much better, so take it.
Okay, so thank you very much, Markus, and congratulations.
Okay, thank you. I now ask Giulio Cerullo to come and chair the last session of today, where the 5 principal investigators will give brief introductions to their work, and then there will be sort of a round table with all of them at the end. Giulio, please go ahead.
Okay. So thank you for staying so long until the last part of this very nice afternoon. So now I'm going to present the project Enhancing Photosynthesis, which is the project that's going to be run by 5 PIs, inspired by the discoveries that have led to this prize. So the idea is to apply a multidisciplinary approach for the study of sunlight capture and manipulation. So the project has 3 objectives. So first of all, understanding the molecular mechanisms of natural photosynthesis and improving the photosynthetic efficiency. applying the design principles that one learns from natural photosynthesis to artificial photosynthesis. And finally, third and also important goal is to establish a local network in Lombardy for the study of natural and artificial photosynthesis, so bringing together several people who share these interests. Now, the project is structured in 5 work packages. Work package 1 deals with investigating the molecular basis of photoprotection to enhance photosynthetic efficiency and improve plant productivity. Second work package is to use barley as a model species to improve the photosynthetic process in crops. Third work package is the use of nanoporous materials as bio-inspired systems for artificial photosynthesis. And these are 3 work packages more dealing with, say, the materials, both natural and artificial. And the last 2 work packages deal with the spectroscopy, so with investigations aimed at understanding the mechanism. And the first the fourth work package is understanding the design principles of photosynthesis from natural complexes to artificial biomimetic materials. So use different spectroscopy techniques with this goal. And then, 5th work package, creation of a joint optical spectroscopy hub for the study of natural and artificial photosynthesis. Now, this project will be run by 5 PIs who will later present briefly their research, their background and their goals. So I will just briefly go through the... well, first of all, this is more or less an overview of the project. So you see that you can cluster the partners in, let's say, 3 groups. There is the group in Università di Milano and Università di Pavia, who deal mostly with natural photosynthesis. The group in Università di Milano Bicocca, dealing with artificial materials for photosynthesis. And finally, the group at Politecnico and CNR, dealing with... yes. Ok, non si vede. Ok, perfetto. Dealing with spectroscopy. Okay, now briefly the 5 PIs. Alberta Pinnola is a professor at Università di Pavia, and her research deals with studying plant evolution to identify and characterize the genetic information used by photosynthetic organisms to survive various light-associated stressing conditions, and elucidating the molecular mechanism of photoprotection, and identify genes that confer boosted photosynthetic capabilities to mosses to enhance productivity in modern plants. Paolo Pesaresi is a professor from Università di Milano. He really is understanding, again, interested in understanding the molecular mechanism underlying the regulation of photosynthesis and chloroplast biogenesis, using in particular the model system Arabidopsis thaliana and barley, and use also really go to the field to use barley to test biotechnological strategies to transform crops into multi-purpose plants. Now, Silvia Bracco is from Università di Studi di Milano Bicocca. She deals with nanostructured materials, in particular MOFs and POPs, and these are used as kind of scaffolds, as building blocks for the fabrication of sophisticated architecture that can be used for light harvesting and luminescence properties. So this can be the basis for doing artificial light harvesting, for supramolecular systems for artificial light harvesting. Now, Margherita Maiuri from Politecnico di Milano works on ultrafast spectroscopy of natural and nanostructured materials, using mainly femtosecond spectroscopy to understand the primary steps leading to, first of all, the energy transfer and then the charge separation, and using this information again for the design of artificial light harvesting systems. And finally, Stefano Santabarbara from the CNR, who has a long experience through many institutions also abroad on spectroscopy, different kind of spectroscopies of photosynthetic system. So Stefano really brings together the expertise in biology and biochemistry with a very deep spectroscopic understanding, which is, I think, very important for this project. So I think this is a very strong, very well assembled team covering really different expertises. And now I would like to ask each one of the PIs to come for maybe not more than 10 minutes to present their background and their goals. So maybe we start with Alberta.
Se no posso stare anche qui seduta.
Forse dunque c'è un pointer, mi sa che c'era Marcella. Tu hai un pointer, Marcella? Non so però se poi va inserito qua dentro per scorrere. Devi inserire, stare qui. Forse conviene stare lì, guarda, per esempio.
Thanks, Giulio, for your nice introduction. Good evening, everyone. And I'm here happy to be here today because I can describe you the work I've done over the years. And also because I can describe you new plans that we have, which are related to this project that we are developing here all together. And for this, I really like to thank the winner of this prize, Lombardia Ricerca. I study natural photosynthesis and processes related to photosynthesis. I don't think to tell you what photosynthesis is, but I will just give you few important features for plant. Photosynthesis uses sunlight to produce, a plant uses sunlight to produce their own nutrients, thanks to photosynthesis. In this process, plant uses CO2 and water, and of course, we are happy because we have the production of oxygen. But plants are not happy in excess light condition. Excess light condition is dangerous for plant. Plants, do they die in excess light condition? Because the chromophore, which are essential for photosynthesis, are bleached because of this excess of light, and in this case, they result in non-productive reaction. By the way, plants evolved mechanism in order to protect the cell from the excess of light. They are called photoprotection mechanism, and in particular, this is the most important one, which is called non-photochemical quenching. This is the ability of plant to dissipate the excess of light into it. Plant continuously need to find a balance among different features, and in particular, between photosynthesis and non-photochemical quenching. Thus, we need to find a balance between photosynthesis and NPQ in order to improve plant productivity. NPQ is a wonderful mechanism. It works very well, but there is a limitation. As we know, sunlight intensity changes a lot in a day. Sunlight intensity changes in a matter of hours, minutes, seconds. And the problem is that NPQ is not very fast to activate itself in high light condition, and also is not very fast to switch off itself in a sunny or in a cloudy day. We can think what happened in a context of a canopy, or for example, in this case, in which we have different leaves. These leaves are located in different layers. In a moment, they have a particular sunlight intensity, but then just a wind blows, and the same leaves is exposed to a completely different light intensity. The limitation is that
photosynthesis and non-photochemical quenching, as we can see in this plot that I'm going to show you, to describe you, is that are not so fast responding over the time. Here in this plot, we have photosynthesis and the time. When a plant is exposed to a normal light, photosynthesis works, and works very well. But when a plant switches from normal light to excess light, photosynthesis decreases. And of course, this decreases because non-photochemical quenching is activated. These are two competitive processes. But when plants switch from excess light to normal light again, we can see here the photosynthesis is very slow to recovery. This is why non-photochemical quenching is very slow to switch it off. This is a waste. If we think that this happens many times in a day, this is a huge waste for plant productivity. This is why we can improve the balance between NPQ and photosynthesis to avoid this waste. And to do that, we need to work at molecular level. What we want to do with our research is to find out every single molecular step which is involved in the process of non-photochemical quenching and NPQ, because in this way we can improve these steps, thus we can improve photosynthetic efficiency. Of course, we are in a very complex biological context. This is a chloroplast. In a leaf, you have many of these chloroplasts. And this is a complex biological complex because the proteins that we study are here. These are thylakoid membrane proteins. And these proteins are embedded in a lipid environment. Not only, but many of these proteins bind chromophore, chlorophyll, and carotenoid. Here you can see an homology model of a protein that we study. The red one is the protein. And this protein, many of these proteins, bind a lot of chromophore. How can we study this protein at molecular level? We need to extract this protein from this biological constant, which are chloroplasts. And to do that, we just use leaves. This is a tobacco plant. We harvest leaves. We purify, we isolate chloroplasts, and we obtain this, we can say, green juice. But these are proteins which need lipid. For this, we need to solubilize this protein using detergent. And then, in order to purify our protein, we can use different methods, chromatography or ultracentrifugation. Here you can see an example of affinity chromatography. This green one is our protein, and we are eluting our protein from many, many, many other proteins. And this is an example of ultracentrifugation in which using a sucrose gradient, we again can purify our protein. At the end, we have our protein in detergent. Recently, we also obtained an outstanding result using this method called nanodisc. These are nanodiscs. Basically, nanodiscs are slices of membrane in a lipid environment. Here we can put our protein. The procedure is quite easy. We have our protein in detergent. We mix our protein with lipid and also with the MSFP, membrane scaffold protein, which is a belt surrounding our nanodisc. This is really a very nice method because in this way we can study our protein, let's say, in a natural environment. At the end, we obtain our protein in a tube test. Here we can see one of the proteins we have studied. This looks actually a really, really few amount of material, but sometimes to obtain this material, we really need to work a lot. Once we have our protein in a test tube, we can make different biophysical measurements. I don't tell anything now about this our measurement because people who are talking after me will tell you something about this kind of measurement. But here I want to show you that using this kind of study, we can find out what happens at molecular level. This is an example of protein that we are studying in mosses. This protein binds chromophore and caroteroid. In particular, in normal light condition, this protein is able to absorb light in order to make photosynthesis. But in high light condition, this protein is able to dissipate the excess of light into it. And using this method, we know how this protein works, because this protein makes a conformational change, and this is because some of the chromophore just exchange depend on the process, photosynthesis or NPQ. Actually, we are studying different kind of protein coming from different organisms, algae, mosses, and higher plant. And we are very, very interested in studying mosses, because mosses are the first organism that emerged for the water to the land environment, which were characterized by different stressing conditions. Mosses are very resilient organisms, and we found out in mosses really interesting protein that can help us to improve photosynthetic efficiency. Our aim is to improve natural photosynthetic efficiency. And I can tell you that this can work, actually. I have some proof of principle on that. Here you can see an higher plant, Arabidopsis thaliana. We introduce in this plant a moss protein, which is called LSCSR. Here you can see the protein. In a stressing light condition, high light stressing condition, our protein is bigger. This implies that we are improving photosynthetic efficiency and plant productivity. Our dream is switch from this situation in which the non-photochemical quenching response, which is the red curve, is delayed with respect to the sunlight intensity, which is the yellow shade, to this situation in which NPQ and sunlight intensity almost perfectly match. I think that we can do that, but how can we do that? We can still study this protein. How? We can mutate, we can find out each single amino acid of the protein, which is responsible for the binding of the different chromophore and the involvement of the chromophore in doing the conformational change. This is what we really want to do with this project. In fact, I will lead the work package number 1, which is, as Giulio told us, is about the improvement of a photoprotection mechanism. And of course, to do that, in order to improve photosynthetic efficiency, we need different kind of expertise. And I am really happy to join to this project because we have a wonderful team. We have different expertise in plant physiology, in biochemistry, in biophysics, and also in chemistry. In particular, what we are going to do in this work package is the generation of protein mutant in order to study the photosynthetic efficiency. I'm going to do that in collaboration with Paolo and me. And also, once we manage to purify it to get our protein mutated, we are going to do biophysical analysis in collaboration with CNR and Polyme. Once we find out the most interesting mutation, the idea is introduce the mutated form, the most interesting mutated form, into plant in order to analyze the photosynthetic efficiency. This is the idea about the work package number 1. And then, of course, the idea is also to combine natural and artificial photosynthesis. And in order to do that, of course, we need chemists. This is why we are really happy to join with the University of Milano Bicocca. And thank you for your attention.
Now, maybe the word to Paolo. Maybe if you want, you can even sit. Maybe better. Tu l'hai già caricata? Sì. Okay.
Posso chiudere questo? Sì. Anche questo qua deve essere questo qui.
Perfetto, dai. Forse è meglio far così.
Sì. Ok. Innanzitutto, many thanks for considering me still a young scientist. So I'm Paolo Pesaresi from the University of Milan. I have my lab a few meters from here, and I start organizing my lab in 2009 when I came back from Germany, where I spent around 10 years, first at the Max Planck Institute of Cologne for plant breeding research, and later on at the Ludwig Maximilian Universität in Munich. I came back to Italy with the famous law of rientro dei cervelli, and since then I had to work a lot to build up my own lab that you can see now here. So as you can see, it's a rather recent picture from the mask. So in my lab, we have three main research lines. We are obviously working photosynthesis with two model organisms, Arabidopsis and barley. And our aim is to understand, obviously, the molecular mechanism of photosynthesis and how this process adapts to environmental changes and also to climate change. And also based on this knowledge, what we wish to do is to develop biotech strategies to increase photosynthetic performance. We have also a third line of research, probably not so interested here. We work with yeast, and here we are trying to develop small peptides of 8 amino acids to interfere with protein activities. And these are used, in our case, as a pesticide, as a sustainable pesticide, as eco-friendly pesticides, to substitute, to replace the conventional pesticides. I can skip this since already Alberta showed something similar. So in my group, we essentially use functional genomics. We use as a model system, as I told you, Arabidopsis. We simply compare control and mutant plants, and then we try to investigate them by using molecular biology and biochemistry, and also by using fluorescence analysis to study their photosynthetic performance. By using this very simple strategy in the last 15 years since the lab was built up, we managed to clarify some important molecular details of what we call short-term adaptive response. I don't have time now to go into details, so we have been able to clarify some important molecular mechanisms concerning state transition. You have heard from Pierre, and I'm honored to have with him some papers about the cyclic electron transport, and also concerning the photosynthesis control. On the other hand, we are also working on what we call long-term response. Short-term, probably understood, means response that need to take place within seconds. For the long-term response, we are meaning something that takes place within minutes, hours, or even days. And here I'm studying mechanisms that are responsible to the biogenesis of chloroplast, or to adapt the chloroplast to particular physiological or developmental needs. You can see from here that if you are going to remove some of the genes that are essential in these processes, you cannot basically recognize anymore the chloroplast. That's our control, and that's what happens if you remove such important genes involved in the maintenance of chloroplast activity or in its own biogenesis. Now, Arabidopsis is a powerful tool, but has major limitations. Obviously, it's not a crop. It's a weed. It's a plant that you would remove from your garden. And of course, it cannot tell you how powerful are your biotech strategies if you just look at Arabidopsis. And the second major limitation of Arabidopsis is that, as you have seen, it grows on a plane. So you don't have a canopy, you don't have a third dimension. That's why we move to a real plant, to a crop, and we select among them barley. Barley nowadays is a very powerful model crop because we have a very good genome that was a sequence, the second draft released in 2019. We can do a lot with barley. We can make a genetic transformation. We can make all possible analysis we wish, also biochemistry, molecular biology, biophysics. But what we can do with barley is to exploit the enormous genetic variability that is present in this crop. We can generate genetic variability by mutagenizing this crop, by chemical mutagenesis. But what is extremely powerful is that we can collect varieties worldwide, sequence the genome of thousands of different varieties collected from different places in the world, and learn how nature adapt photosynthesis to the different environmental scenarios. So there are probably solutions already developed in nature, and profiting of the fact that we can quickly sequence all these varieties, we might learn by looking at their genes, at their genomes. So we are going to exploit this variability using the classical functional genomic approaches. We run experiments in what we call forward genetics. So we saw out barley plants in the field, and then we screen for phenotype of interest by using very simple tools like can be a fluorometer to measure the photosynthetic efficiency, and then screening we get the mutants that we wish to have. One of the mutants we will bring into this project is this mutant here. We call it happy under the sun as one because it feels to stay very well in under highlight conditions. And we selected this phenotype based on a strategy that was quite well developed in cyanobacteria and microalgae grown in bioreactors. This concept comes mainly from the work, very elegant work made by Anastasis Melis and at the lab of Roberto Bassi in Verona. They were able to show that if you have dark green cells, the photosynthesis in a bioreactor will be run just on the cells on the surface of the bioreactors. A lot of this energy actually will be dissipated, will generate photooxidative damages, and only a fraction will be used for photosynthesis. All the rest will be in the dark and will not run photosynthesis, and this will be a rather inefficient system. If you just reduce the chlorophyll, the antenna proteins that bind the chlorophyll, then this light will penetrate towards the bioreactor, and that will allow to have also the other cells to make photosynthesis, and the entire systems will become more efficient. There is no doubt that this strategy, it works. It works in cyanobacteria and microalgae. Does it work in crops? That's what something we wish to test with barley. We have already some field trials using these pale green plants. The idea here is the same. Having pale green plants, the light would penetrate towards the canopy, and those leaves that will usually remain in the dark and will not perform photosynthesis, they will they will be able to have light and perform a better photosynthesis. Pale green color has many other advantages. Obviously, the leaves on top of the canopy that will receive most of the light will have less probability to go into photooxidation. And there are modelers, there are several papers from modelers that sustain that if we turn our agriculture into pale green crops, it's like to build up a mirror on the surface of our planet, and we could even reduce the temperature at the soil level of 1.5 degrees. So it's a way also to mitigate climate change. In this project, beside that, we will also start a new research line that is dedicated to the non-photochemical quenching. I don't have now, I don't need to introduce this concept. You have already heard about it. So what we want to do essentially is to make it more efficient. If this is the activation and inactivation process of these mechanisms that protect plants from excess of light, we would like to turn it on the left. make it more rapidly active, and at the same time, we would like to, that this is inactivated immediately, the highlight turns into a low light. How to do that? The solution we suggest is actually to exploit this genetic variability and to look if some solution already exists in nature. I make you an example. What we do here is we know as I told you, the genome sequence of many varieties collected worldwide, and since we know the genes and the proteins that are involved in this mechanism, we are going to look at the sequence of these genes and of this protein and see whether these sequences are changing according to the environment where we have isolated these plants. So it's just a matter of nucleotides and, of course, of amino acids in the corresponding protein. And I can tell you there is plenty of genetic variability. This is one of the genes involved in this NMPQ, and you can see how many SNPs, single nucleotide polymorphism, we can get within this single gene. Obviously, many of them will not make any change to the enzyme because, as you see, they are into introns. But anytime these modifications are into the hexon, into the coding sequence of the gene, then you replace an amino acid with another, and you change the activity of the enzymes. The very nice thing of that is that you might think that if you change amino acid, you lose in the stability of the protein. But obviously, these are solutions adapted by nature, invented by nature, and these changes do not modify the amount of protein into the chloroplast. It just modifies the activity of the enzyme. So essentially, we don't have to imagine, to guess which amino acid we have to change. Nature has already done for us. And the same is true for the other enzymes. That's what we wanted to investigate, and these lines will be obviously analyzed in detail by profiting of the expertise of Stefano and Margherita and Alberta. I want to leave and profit of the occasion that I have here to talk in this prestigious institution to tell you the fact that, of course, we can improve photosynthesis, but this is not enough. We need to have a sustainable improvement of photosynthesis. If we improve photosynthesis, we hope to have an increased amount of biomass in terms of straw and in terms of grain. And, of course, we will have a lot of straw, and we need to use this straw if we want to have a sustainable agriculture. I spent several weeks discussing with companies of what kind of straw would you need so that this straw could be used in the industry market. And we found the industry that they were asking us, we need a straw with an increase in nitrogen so that we can use for feeding animals. There are many companies that would like to have from us straw with different content of lignins, from very low lignin amount, and so we bring it into bioraffinery for producing biofuels. But there are many companies that are asking us to have a straw with a high content of lignin because they will be used for the green building sectors, from the interior design, for the automotive sector. They want to use this fiber to replace plastic, essentially. And there are also companies coming especially from the cosmetic sectors that would like to use waxes produced by barley to replace the waxes that are normally obtained from bees. What we need, we are sure that we have all this genetic variability in our collection. What we need, and this is a request that I do to Margherita, but in general to Politecnico, we need sensors. We need the ability to move in our fields with sensors that can tell you in a high throughput way, in a non-invasive way, in a very rapid way, which are the lines with the characteristics we wish. And then we can pick up, analyze, and combine eventually this trait in order to have a new generation of crops where we use the grain for animal and human nutrition, but we also don't leave the straw in the field, but at least part of it we can take and bring into the industrial sector. So I'm really proud to be part of this project. I think this will be a very first step towards a new generation of crops for agriculture. So I hope really, I'm pretty sure that will be a quite exciting project. And I wanted to finish, obviously, to thank Regione Lombardia and Lombardia Ricerca, and obviously the 3 winners for selecting my group for contributing to this project. And many thanks for you for your attention.
Many thanks. And now we move to Silvia. Vediamo se riusciamo a stare un po' nei 10 minuti. Sì. Dai qui.
Okay, so first of all, I'd like to thank the 3 winners for giving me the opportunity to contribute to this challenging project. And my research activity is focused on the design and construction of nanoporous materials with several aims. In particular, I'm dealing with porous molecular crystals, porous organic polymers, and metal organic frameworks. And these materials play an important role in the field of separation of gas and selectivity in the gas absorption, and in the gas storage, in particular for hydrogen, methane, and for carbon dioxide capture. These materials can be always exploited as nanoreactors, for example, for the polymerization in the confined state. And another important aspect is the dynamics of moieties inside the porous structures. In fact, the structure flexibility can modulate the confining of gas molecules and, for example, can modulate the adsorption properties of these materials. And we can also incorporate chromophores inside the porous structure, and so we can promote interaction with light. So in metal organic frameworks, the building units are constituted by organic linkers and metal ions or clusters. And the synthetic process is made by 3 steps. The synthesis of functional linkers, the self-assembly with the metal ions, and then the removal of gas molecule. And all these 3 steps are equally important because the precise control of the entire process can make possible to prepare, to create crystalline structure with the porosity. And also we can modulate the architecture that we can prepare by changing the organic linkers and the metal ions. So a key aspect is the crystal purity of the structure that we can prepare, we can create. And so we can use X-ray diffraction method or solid-state NMR techniques for verifying it. For example, we can starting from conjugated aromatic units as linkers, so like DPA, diphenylanthracene, and with the zirconium ion create a crystalline structure here presented in the bottom part. So we can, for example, here appreciate that we have 2 different kind of cavities in tetrahedral and octahedral with a distinct dimension size. the surface area of these materials, as shown by the nitrogen absorption, is very high. We are about, it is about 3,000 meters square per gram. And this feature is very important, is a great advantage for the hydrogen uptake. And in this particular case, this MOF shows a high uptake of hydrogen. As regards CO2 capture, I present here a molecular system based on sulfonate organoanion, and amidinium cation, and we can see the porous structure here presented. And this particular material presents a very high efficiency in terms of absorption of CO2. And in particular, we can observe here that in the same condition, the nitrogen is not absorbed, while the CO2 presents a very high uptake. And we can so deduce that the selectivity of carbon dioxide over nitrogen is extremely high for this kind of material. The direct detection of carbon dioxide is made by a solid-state NMR. So we can perform this kind of experiment, two-dimensional NMR experiments, and we can recognize specific interactions between the gas inside the nanocavities and the amidinium groups, as shown here along the red line. Another NMR technique that we can use for studying these porous materials is the hyperpolarized xenon NMR. In this case, we can obtain important information about the open porosity of our systems, the size and the shape of the cavities, and from the point of view of xenon gas diffusing inside these nanostructured porous materials. So, as regards optic properties, we succeeded in the incorporation of DPA, so diphenyl anthracene, and metalloporphyrin chromophores inside a very robust covalent porous organic polymer. In this case, we observed, from the point of view of photophysical properties of the materials, the conversion of low energy light into high energy photons through the phenomenon of triplet up conversion. Photoresponsive aromatic units could be incorporated in porous organic polymers. And in this case, we observed that we can modulate the CO2 absorption on command, so by irradiation of the materials. As last example, I show you that we have synthesized a luminescent MOF nanocrystals. In this case, the nanocrystals is based also in this case by DPA linker, and the use of high atomic mass of the metal, so in this case we've used zirconium, and the stability of these metal organic frameworks in water can result as an added value for the artificial photosynthesis that we have to explore during the project. So, based on our toolbox for synthesis and characterization of this kind of materials, we will design photoactive metal organic frameworks and photoactive porous organic polymers. So for creating a bio-inspired system for artificial polymerization, photosynthesis. For doing that, polyconjugated aromatic linkers, porphyrins, and organic functional groups will be incorporated in the scaffold, in the porous structure of our materials for creating something like antenna in the photosynthesis. For the synthesis of, for the preparation of MOF, we could also use different metal ions and so try the properties in the different cases. After a complete characterization of these materials in our laboratories, we will send we will deliver the material to the other unit. And in particular, we will characterize the materials paying attention to the water stability and water adsorption detection in these particular materials. So we will send the sample to University of Milano and Pavia for create interaction with the biological world and compare the properties of artificial material with the biological system. And the materials will be sent also to Polytechnic and CNR for the performing of ultrafast spectroscopic observation, so advanced spectroscopic observation on the photoactive MOF and POPs before and after the inclusion of a photocatalytic complex. I'd like to describe a little bit our group, our research group, because I didn't create a slide for that. So I'm working in the Department of Material Science of University of Milano Bicocca with Angelina Comotti, Professor Piero Sozzani, and several postdoc and PhD and undergraduate students, and I'd like to mention Jacopo Perego for the synthesis activity, and Charles Bezenwidaut for the computational analysis. And I thank you for your kind attention. Thank you.
So now we move to the fourth presentation by Margherita Maiuri.
Thank you for the kind introduction, and thank you for sticking around so late. Okay, so I work here at the physics department, and I deal with ultrafast optics. So I would like to briefly tell you a little bit of the things that we can do in our group and what would be our role here. So why we need ultrafast optics, and let's start from a sort of a very general example. So how fast we can see. So if I kind of ask you if you want to really follow something in motion, what would you need if our visual perception is not enough? We can take pictures, okay? And so the idea is that if we start from a sort of a macroscopic world and we want to work out the sort of time scale and space scale, we basically end up in staying in a centimeter and then millisecond range. But if we move to the atomic motion and we work out the same kind of math here, we start from having bonds and dimensions, which is basically the atomic scale of nanometers and angstrom. And by working out the speed velocity, we end up staying in this very tiny number. You can see how many zeros are there. This is femtosecond time scale. And this is the sort of time scale under which the action of a molecule happens. So the sort of processes that we can study here basically range from the femtosecond dynamics, where we have absorption of emission of light, and then vibrational motions or electronic dephasing, and sort of interactions which basically deals with charge and energy transfer, which is sort of the main mechanism that we are interested in studying. And then by the time is passing by, we move from the femtosecond time scale up to the pico and then the nanosecond, ranging out the what we call a very long time scale, which is actually the time scale of biology here, which is like microseconds or even milliseconds, where actually dark states happen. So study the dynamics of triplets or radicals or the happening of traps. And so how we can take our picture? So we basically apply sort of a time-resolved optical techniques, which we call, which is called transient absorption of palm probe. So just to give you an idea, you can imagine that you have a very short femtosecond light pulses which excite your sample. And so you can imagine that we have a molecule in a certain state, and it's like kicking the motion of something microscopic, like a horse galloping, for example. And then we can come with a sequence of different optical pulses here, and then really trace basically the absorption of the system and sort of following up the motion of our molecules. So for example, here you can see the isomerization of the rhodopsin, which is the molecule responsible on the vision in our eyes. And you see all these arrows here are basically reproducing the absorption and emission of photons. And so the sort of pictures that we take look like these. So it's sort of bidimensional maps where we have one dimension of the time evolution and then the other one, which is the energy, which is really can relate the process to the molecules. And so how our technique would be useful in this sort of network that we are all very excited to be part of. And so I'll take this chance to thank the Regione Lombardia and then the awardees here, Marcella and Markus, especially, which are present now, to give us all the opportunity to work together and enhance not only photosynthesis but also our network. So thank you very much. And so some of the things that we can do, basically, is to really unveil the first processes in nature. And we've seen many cartoons, like the one that I'm going to show you right now, and so I don't want to spend more time on these, but the idea is that we can really separate the events at the very fundamental level under 3 steps. So we need to have something that absorbs sunlight, and we learn that as much as broad it can be, the better it would be in terms of solar coverage. And then we have a series of sequences of energy transfer. So you've seen like antennas, and Marcella explained this very nicely, wonderfully actually, to us before, that we need to funnel the energy into a sort of a reaction center where actually the real charge separation events occur. And this is the moment where maybe we can interface catalysts and other things to run not only the ultrafast part, but also like the real photocatalytic actions. And so we spent quite some time, and as I said before, these are the sort of pictures that we can reproduce to study these phenomena. You can see the time scale. Something happens on a really few tenths of femtosecond, and then we can follow the evolutions and the energy transfer and charge separation among all of these schemes. This is an antenna protein taken at room temperature, so we can study the system in their biological environment, for example. And also Alberta showed before the cofactors, so which are the molecules really responsible of these absorptions, which are carotenoids and chlorophyll mainly. And so there is really an interplay of how all these proteins and chromophores can act together, and we can really understand the very early steps. So what happens right after a solar photon can be absorbed by these molecules. And as I said, I spent quite some time in understanding these very fundamental processes, and now we can define a sort of criteria. These are just few of the ones that we can focus on, under which we can then use this criteria to define some of the mechanisms and why makes photosynthesis so efficient. And so we know that we need a sort of a collective effect, this antenna system, what actually means is that we need to have multiple chromophores like chlorophylls, and they have to basically sustain and transport the energy. And then we need to have a very efficient separation of the charges, so we need to extract charges on a very fast time scale, so efficiently. And then there is this last, let's say, criteria that is the one actually that I'll be more interested in exploring over the network and this process, which is basically studying the interplay of the role that the molecules can get coupled together. So why this aggregation effect, again, Marcella explained us before, it's working so well. And so starting from this sort of criteria, I also spent quite some time in exploring few strategies and synthetic approaches in such a way that you can basically try to explore some of the fundamental mechanisms that I mentioned to you, so energy and electron transfer into artificial systems. So these sort of dyads and triads are not found in proteins, but you can study them in cuvettes, in a solvent, for example. And so we have such system. We explored something more fancy with phthalocyanine and perilene, and very recently we also moved towards larger aggregates, for example, going towards this idea that aggregation seems to be one key, for example, to sustain the transport. And so within the network, again, I want to highlight this multidisciplinary aspect. So you've seen this slide with all the title of our work packages many times now. And the point would be that our unit here in Milano will basically work in contact with all of the other partners from the Paolo and Alberta and Silvia that already presented. And you'll hear now Stefano describing this very interesting idea also of trying to create a hub which will basically survive even after the duration of the project. So we definitely are going to characterize our system, both on the biological and the artificial side. And as I said, I'll be very interested in leading these work package number 4, which is basically deals with the idea, very intriguing, of exploring potentially quantum effect. And why we believe that this could be a criteria. When I was a postdoc in Princeton, we spent quite some time in exploiting mutagenesis, for example, to understand the role that vibrations can play into basically capturing sunlight and then shape the energy towards this basically functionalization that we want to have. What it's still not clear if these vibrations do really play a role in a sort of a biological functions. But we know that in some artificial system, which is not a photosynthetic antenna, artificial biomimetic, but it's actually a blend, which is a polymer foolery system for photovoltaics application, we found out, and this is a sort of a molecular movies that our collaborator made out our spectroscopical characterization, that the charge separation here, it's really sustained within few hundreds of femtosecond by this idea of having strong vibrations. And so expiring both by these studies on biological system and sort of artificial light harvesting, we will start from the natural complexes, and then we're going to study and try to explore the role that vibronic coherences, and so this interplay between, again, vibrations of the molecules and then the coupling, the electronic coupling of the different chromophores that are present in the photosynthetic antennas and reaction center can play a role. And we will work in close contact, especially with Alberta and Stefano, that we talk after, that basically have the tool to exploit mutagenesis. And then for the biomimetic side, you heard what Silvia can do with a very nice approach and their structures. And so the idea would be first to test the functionalization of some of her structures and then explore, because this is definitely going to be more an exploratory phase, if some of these criteria can then be exploited for enhancing some of these functionality. So with that, I'd like again to thank everybody, and thank you again for this chance to work all together. I hope it was important.
Thanks a lot, Margherita. And now we move to the last presentation given by Stefano Santabarbara. L'ho già caricato stasera.
indietro così, vero? Ok. Okay, so thank you very much for considering me for being involved in this project. It of course makes me very happy. It makes me very happy that we have a chance to work on the photosynthetic process jointly with colleagues, some of which we were working together before, some of which are new and extending the network, and hopefully that will remain like as a collaboration also for the future. So like tuck, I'm never very good with this. Okay, I'll sit down, maybe it's better. As we heard, like of the photosynthesis converts light into energy, into another form of chemical energy. It does that in the photosystems. Here is an example, but an example I'm showing photosystem 1, but there are some differences in between the photosystems, but the photosystems also share some very common principle of operation, and that's you see they are very complicated objects which have a lot of molecules of chromophores and proteins. Here I've removed the protein, also the chromophore are left, and still quite a hell of a lot. But of those, only a very small part is the part which actually performs photochemistry. So in a very schematic way, it could be seen as a lattice with a defect which is capable of doing something. The systems are very efficient because energy transfer to the reaction center is very efficient, and the reaction center itself converts the excited state into charge-separated state very efficiently. So to have an efficient system, both of light capture and photoconversion in nature, you need both processes to be efficient. Now I will focus a little bit on the charge separation and electron transfer, which we haven't heard at all much in the natural system at all. I use PS1 again as an example, but apart from some technical difference, that's the same. The way the system works, that like starts from an excited state. Normally that comes from like some chlorophylls which are more or less strongly excitonically coupled in the reaction center, which is generally composed by 6 chromophores. And you can form like initially a charge-separated state with a plus sitting on one of the two, on one molecule, and an ion sitting on the other molecule. And then rapidly the anion is taken away by a cascade of electron transfer event from the cation, and this decreases the chance of a recombination. Like on a very general terms, you can see the cascade of donor acceptors, which follows like a gradient in energy. This is the drive for the reaction. They are getting further separated, and so they recombine slower and slower and slower. And as soon as the recombination is much slower than the excited state lifetime, which is normally in the order of a few nanoseconds, you can consider the charge as separated and stabilized. So this is what we wanted to explore, basically. And we have 2 examples from nature, basically, which are type 1 and type 2 reaction center in oxygenic photosynthesis, the photosystem 1 and photosystem 2. They are both very efficient, but photosystem 1 is significantly more efficient than photosystem 2. However, photosystem 1 somehow does like a simple chemistry, because everything which happens in photosystem 1 are one electron transfer events. Instead, photosystem 2 accumulates electron both at the accept and donor side. So that probably this loss of efficiency is a price that the system has to pay to do some complicated chemistry. There is also like, okay, that's what I just said. There is also one characteristic which differentiates the 2 photosystems, that in PS1 both electron transfer cofactor chains are functional, whereas in photosystem 2 only one. Actually, the notion comes from the bacterial reaction center, where people have tried very hard to make the unfunctional branch be functional, hardly ever succeeding. So like, it's been like contentious if photosystem 1 branches were both functional, Part of the work I've done in the past was exactly to demonstrate that. And I come back to what Pierre said, that I was very convinced our results were correct because I assumed that only one branch should work. And when we get results which could not be explained other than both branches be working, then I disproved myself and I was happy with that. So I show an example of this data. These were done by applying pulse electron magnetic pulse CPR to mutants of the PS1 reaction center subunit, which affect the coordination of these cofactors. So this is an example. These cofactors got an unusual coordination, which is from a methionine. Most chlorophyll in proteins are coordinated by histidines. And in fact, the mutants we study is an exchange from methionine to histidine. That's not really important. This is the theory of the technique that we used. This is called out-of-phase electron spin envelope modulation. This is only something which is observed on radical pair state because standard EZIM, which is in phase, is instead hyperfine resolve spectroscopy. It's a pure quantum effect, which is also long-lasting. It's dominated by dipolar exchange interaction, and from the dipolar interaction, you can calculate the distance in between the radical pair states. So when we mutate this chlorophyll specifically, these are the traces we get, these are the fits, and we got a distance of 25.4 angstrom, which very high precision. That's thanks to these measurements were done in London, and the analysis was performed with colleagues in Oxford. And this distance is very nicely matched distance in between one of the two kinone, the one on the PSA subunit, and the one on P+, assuming an asymmetric distribution for P+, which we know from independent TPR measurement. If we mutate the other chlorophyll, we see a different modulation, and this corresponds to this distance. And now there is no other explanation for this other than having the both branch functionally. And in a situation in which you basically prevent the electron to go on these cofactors, so they can only stop here, you can observe both modulation the wild type. So I think this pretty nicely shows that you have both branch functioning. And to observe this effect, the electron must travel through A node. So they cannot go through another path, otherwise we lose the signal. However, both branches were functional, but they're not identical. This was proved actually in Pierre's lab using transient absorption spectroscopy in the UEVs. I work on that too, and I show you this an example of two things which looks very, very similar, but they're not the same. Again, this is a proof of both branch functioning. So if I mutate something which is around this kinone, this is the wild type, this is the effect of the mutants. You see that you have the reoxidation kinetics are biphasics. One of the two rates goes lower, only one of the two. The other one remains more or less the same, Pliat is the same. If I change this other one, I have the opposite effect. This one stays the same, this one gets lower. And this is, again, an explanation of what's happening. Now, what we have, which is curious, is we have something which is very, very similar on between the two sides. But, for sure. Some which is very similar on the two sides, but is the rates differ by about an order of magnitude. So how do we explain that? This is some work that also I work. So we try to rationalize the system by using electron transfer theory. And here are the frequencies that Margherita was talking about, which comes into the equation within the function we described, the Frank-Condon factor. This is often forgotten, but in classic electron transfer in protein, there is no diffusion of the cofactors. They cannot get to contact. So for the electrons or the holes to move, you will have to go through a potential barrier, and the only way to do that is to have tunneling. And so, and tunneling is also efficient because you have it coupled to vibrations. This is a very simple formalism which considers just one mean mode, but you can have many modes description. There's one mean mode work. This is just an example. We came out with this difference in the energetics. So you have one electron transfer step which is slightly uphill, one which is downhill. with a common value for the organization, and just a weak couple mode is around 275 centimeters to the -1. And with that, we can describe all the system. Take it with a pinch of salt, but it's a good description. So this is something I worked on. I want to show the reaction center. There is plenty of things that we can do, and we can tune the reactions. By using the model, for example, we can simulate many different mutants very satisfactory, just by tuning of the redox reactivity of the cofactor. This is our type of contribution we would like to give to the work package, which will be mainly coordinated by Margherita. We'll be like working on the natural system by modifying the protein cofactor interaction, which to us acts as a non-isotropic solvent for the cofactor. So to see like a non-isotropic solvent can control the reactivity of things. And moreover, we would like the one which have been put in charge was to coordinate the establishment of a spectroscopic hub, which should have like a broad range of methods joined together to be able to study natural and artificial photosynthesis under different points of view. You need that because photosynthesis moves both the natural and the artificial through a very broad range of scales. So like there is no a single approach which will solve all the processes that you might be interested in. You will have to match some that we have. Let's say that the polytechnics have got a range of very fast techniques, and we have a range of much slower techniques. So these are some of the examples. We can have transient absorption, two-dimensional electronic absorption, with modeling, and eventually this is unpublished modeling of 2D decay-associated spectra. We can have, at the CNR, we have like a lifetime for excited state and TSPC. The Polytechnic, they have strict camera. They are complementary techniques. We can analysis modeling and start information, and so on. And also interesting, like the CNR, we have like a Joliot type spectrometer, which, as Pierre said, I totally agree. This is a very flexible machine, and often to want to address a specific question, you have to have the instrumentation which allowed you to be able to do so. This is becoming more and more difficult to do, to get funding, especially in Italy, to develop instrumentation. So I think that here we will have a chance to improve what we already have, to make it also usable, not only for what it was designed at the beginning, but also applied to material and solid state. And that's basically that. And I would like to thank you very much for everything and patience.
Thanks a lot, Stefano. So let me thank all the speakers for this really nice presentation. So we are coming now to the end of our event. It was a very long, very interesting, but also very long afternoon. So I thank you all for staying so late and listening to all these talks. So I would propose, since it's already quite late, if there are no pressing questions for the presenters, we may maybe close here this event. And I would like to thank everybody for, first of all, the winners of the prize Lombardia Ricerca, for giving us some really inspiring lectures, and also the PIs of the projects for really showing the breadth of research, interdisciplinary research, that really has the potential to create a network, a hub that will make an impact on this very important field. So Andrea, would you like to add a few words to close this event?
I'd just like to thank you, Giulio, for organizing this afternoon. It's the first time that Premio Lombardia Ricerca actually does not just the footballers and the, Jerry Scotti, but we also have the science about it, which is fine. So maybe if Jerry Scotti is the ambassador for research, we can be the ambassador for arts and, spectacle. And anyway, I mean, this was very interesting, and I also think it's the first time that by the day when the prize is awarded, the project is defined. There are so many different institutions in Lombardy involved in it. And as said many times, I can see the seed of something that can stay in the long period of time. And now Marcella and the others that you are so famous and well-known ring the minister and ask her in the PNRR, we need a little bit of money for this. I remind you there's about 7 billion euros to be spent, so please try to get your share of it. Don't be shy. If you're shy, the money goes to somebody else. And Marcella in particular in Italy, not that I have anything against Markus, but being an Italian minister is easy. You have the link with them and also the link with the Regione Lombardia, who, as you listened this morning, has also plenty of money to spend. So my advice is when you want money, you need to ask it very insistently and speak with the people who have the money so you can get some of it. So this is the beginning of something very big, and you can get it funded in the long term, I'm sure. And the science will be good. The science is always good. Thank you very much. Goodbye.